far beyond the planets we dream of reaching, past every star we've ever mapped, lies a reality scientists can't escape. The Milky Way isn't just our home, it's a gravitational fortress, a structure so massive, so tightly bound, and so dominated by forces we barely control, that even our fastest machines cannot break free from it. Every star, every cloud of gas, even the sun, is locked inside an invisible grip that stretches across 100,000 light-years. Today, we're diving into the science that explains why humanity may explore worlds, travel between stars, and build civilizations across the galaxy, but will almost certainly never leave it. The Milky Way, our cosmic home. The Milky Way is the only galaxy humanity has ever known from the inside, yet for most of our history, it was nothing more than a soft white band across the night sky. It took centuries of observation before scientists realized that this pale smear of light was not a cloud or a trick of the atmosphere, but a vast star system stretching across 100,000 light-years. Inside this system, the sun moves with millions of other stars, all bound by gravity that reaches far beyond anything we feel on Earth. When people talk about our cosmic home, they usually imagine the solar system, but the true home of humanity is this enormous rotating disk of stars, gas, dust, and invisible mass that shapes every orbit and every beam of light crossing the sky. The Milky Way is a spiral galaxy with a structure that looks simple when drawn on paper, but reveals a complex and living system when studied with real measurements. The Milky Way stretches across the universe as a huge, star-filled island of matter, bound together by gravity so strong and so persistent that it controls everything within it on a scale the human mind struggles to grasp. When astronomers describe it as a spiral galaxy, the word spiral only hints at what it truly is. From above, the Milky Way forms a vast whirlpool of stars, dust, gas, and dark matter, rotating slowly yet powerfully around a center that holds a supermassive black hole. From the side, it becomes a thin disk with a bulging core and a surrounding halo that extends far beyond what the eye can detect. Every part of this structure follows the same basic law. Gravity binds the galaxy together and prevents anything inside it from freely drifting away. At the heart of the Milky Way lies the bulge, a thick and densely populated region shaped somewhat like a sphere that has been slightly flattened. This bulge is filled with ancient stars that orbit chaotically around Sagittarius A*, the supermassive black hole whose mass equals more than 4 million suns. The stars near this region move at incredible speeds, and their orbits twist and bend in complicated shapes because the gravitational forces near the galactic center are so intense. The bulge is the oldest part of our galaxy, containing stars that formed during the earliest chapters of the Milky Way's life, long before the Sun existed. Extending outward from the bulge is the disk, the most recognizable part of the Milky Way. This disk contains the spiral arms, which sweep outward in enormous arcs that wrap around the galaxy like slow waves frozen in time. Each arm holds billions of stars, along with clouds of dust and cold hydrogen gas that give birth to new suns. The disk is thin when compared to its width, a bit like a cosmic river stretched out for more than 100,000 light-years, while maintaining a vertical thickness of only a few thousand light-years. Within this disk lies the Orion Arm, a minor spiral feature where the Sun resides. Our solar system moves together with the other stars of this arm as the entire galaxy rotates. Above and below the disk exists the halo, a vast and diffuse region containing sparse but ancient stars, along with the mysterious dark matter that forms an invisible envelope around the entire galaxy. Scientists cannot see dark matter directly since it gives off no light, but they detect its presence through its gravitational influence on stars and gas. The halo spreads far beyond the visible disk, expanding the Milky Way's true gravitational size to a diameter much larger than the region where stars are concentrated. The halo's mass, especially its dark matter component, makes the galaxy a stronger gravitational system than it would appear from visible light alone. The Sun sits roughly 27,000 light-years from Sagittarius A*, which places it well inside the disk, but far enough from the dangerous galactic center that life could evolve in relative stability. This distance gives the Sun a balance between motion and safety. It does not orbit too slowly to drift inward, nor too quickly to swing into regions filled with intense radiation. The Orion Arm provides a quiet neighborhood for our solar system, surrounded by other stars that form constellations familiar from Earth. As the Sun travels around the Milky Way at hundreds of thousands of kilometers per hour, it pulls Earth and the other planets with it on a journey that takes approximately 230 million years to complete a full orbit around the galaxy. The movement of stars and gas throughout the Milky Way is not a gentle glide. It is a complex system of gravitational interactions that shift over millions of years. The gas in the disk flows along the spiral arms, compressed by shock waves that can trigger star formation. Young stars form within these dense regions and then drift away as they age, spreading throughout the galaxy. Older stars orbit with different speeds depending on their distance from the center, creating a rotational pattern that puzzled astronomers for decades until dark matter was introduced as an explanation. Without dark matter, the outer regions of the Milky Way would rotate so quickly that they would fly apart. The fact that they do not means that a hidden mass is holding them in place, exerting a steady gravitational pull that keeps the galaxy intact. The Milky Way rotates as a single system, but its rotation is not like a solid wheel turning in one piece. It behaves more like a collection of objects orbiting a shared center of mass, each at a speed determined by its distance from the galactic core and the distribution of mass around it. Stars closer to the center orbit faster because they experience stronger gravitational forces, while stars farther out orbit more slowly. Yet beyond a certain distance, the speed of stars does not decrease the way classical physics predict. Instead, their speed levels off, a phenomenon discovered when scientists compared observed rotation curves with theoretical predictions. This difference revealed the presence of the galaxy's dark matter halo, whose gravity gives outer stars the extra force needed to maintain their higher speeds without being thrown outward. Understanding these movements required centuries of observations and breakthroughs that gradually built a three-dimensional understanding of the galaxy. Early astronomers could only see what was possible from Earth's perspective, a streak of faint light across the night sky that they called the Milky Way, not knowing that it contained hundreds of billions of stars. Over time, better telescopes revealed clusters, nebulae, and starfields that hinted at a larger structure. Once photography became available, astronomers could capture long exposures that showed cloud-like regions made of countless stars, allowing them to begin mapping the galaxy with greater accuracy. The real transformation came with space telescopes such as Hubble, which delivered high-resolution images of distant stars and nebulae without the distortion caused by Earth's atmosphere. Hubble provided data that revealed the structure of the Milky Way's spiral arms, star populations, and the distribution of interstellar dust. It also allowed astronomers to observe variable stars in remote regions of the galaxy, which helped measure distances more accurately than ever before. In recent years, the Gaia spacecraft has revolutionized the study of our galaxy. Gaia is a European Space Agency mission designed to create the most precise three-dimensional map of the Milky Way ever attempted. It measures the positions, distances, and motions of more than 1 billion stars with extraordinary accuracy. These data allow scientists to track how stars move through space, which in turn reveals the gravitational structure of the galaxy. Gaia's measurements have helped astronomers uncover new details about the galaxy's spiral arms, star clusters, and the motions of stars near the halo. It has also detected streams of stars that are remnants of smaller galaxies consumed by the Milky Way long ago, offering a clear history of galactic mergers that shaped our current structure. The combination of Gaia's star tracking and Hubble's deep imaging has given scientists a view of the Milky Way that was impossible in previous generations. These observations produce models that show how stars orbit the galactic center, how gas clouds drift and collide, and how dark matter influences everything. In some regions, Gaia has even detected the tiny, wobbling motions of stars caused by unseen masses, a fine detail that provides direct evidence for dark matter concentrations around the galaxy. Another important part of the Milky Way's structure is the dark matter envelope that surrounds it. This halo extends far beyond the visible stars, perhaps more than 200,000 light-years across. Dark matter does not interact with electromagnetic radiation, meaning it cannot be seen with telescopes in any wavelength. Its presence is known only through its gravitational effect. The halo's mass outweighs the visible matter in the galaxy by a large margin, providing the gravitational pull that determines the rotation speeds of stars and gas. Without the dark matter halo, the Milky Way's disk would not be stable. stars in the outer parts of the galaxy would drift away, and the spiral structure would weaken or disappear. Dark matter acts as the framework that holds the galaxy together and shapes its movement. While the Milky Way's structure appears calm when described on large scales, every part of it is in motion. Stars orbit the galactic center, gas flows through the spiral arms, and the entire galaxy itself moves through the universe, along with the rest of the local group of galaxies. Inside the spiral arms, regions of gas collapse under gravity to form new stars, which eventually disperse their elements back into space through stellar winds and supernova explosions. These processes enrich the galaxy with heavier elements, which become part of the next generation of stars and planets. In this way, the Milky Way constantly evolves. Despite all of this movement, nothing inside the Milky Way moves fast enough to escape its gravitational pull. The concept that defines this is known as galactic escape velocity. In simple terms, this is the speed required for an object to leave the gravitational influence of the entire galaxy and never return. Near the Sun's location in the Orion Arm, the escape velocity is around 500 to 600 kilometers per second. This speed is far greater than anything humans have ever produced. The fastest spacecraft ever launched, the Parker Solar Probe, can reach speeds of about 200 kilometers per second when slingshotting close to the Sun. Yet even that is nowhere near fast enough to break free of the Milky Way's gravity. Escape velocity increases as you move toward the center of the galaxy because the gravitational field becomes stronger. Near the bulge, the escape speed rises dramatically, making it almost impossible for anything to leave that region unless it receives a significant boost from a dynamic event, such as a close encounter with the supermassive black hole. Even stars that achieve escape velocities only do so under unusual circumstances. Some stars, called hypervelocity stars, are flung out of the galaxy after interacting with Sagittarius A star. These rare events occur when binary star systems pass too close to the black hole. One star gets captured, while the other is slingshotted outward at extreme speeds, sometimes fast enough to escape entirely. Although this demonstrates that escape is theoretically possible, the process is violent and unpredictable and cannot be replicated by technology with anything close to the necessary power. As scientists continue to use new technologies such as Gaia's 3D mapping and Hubble's deep imaging, the understanding of the Milky Way becomes more detailed and precise. These observations reveal a galaxy dominated by gravity at every level, from the local movement of individual stars to the broad rotation of the spiral arms and the massive influence of the dark matter halo. Gravity acts as an invisible force holding everything in place, dictating the structure and the motions that shape the galaxy over billions of years. This gravitational binding is the reason the Milky Way remains a cohesive system, rather than a loose cloud of stars scattered across space. The deeper astronomers look into the Milky Way's structure, the clearer the limits become for anything that tries to escape it. The galaxy's sheer mass creates a gravitational environment that extends far beyond what can be seen, binding stars and gas within its enormous reach. Every part of the Milky Way is connected by this invisible force, and every object within it feels its pull. The escape velocity required to break free is one of the clearest indicators of how powerful that grip is and how deeply humans are embedded in the structure of their cosmic home. Even though the halo is mostly empty space, it reaches hundreds of thousands of light years from the center, making the Milky Way far larger than early astronomers ever imagined. The Sun's location inside this enormous structure is surprisingly modest. It sits about 27,000 light-years from the center, orbiting inside a small section called the Orion Arm. This arm is not one of the dominant spiral arms like the Perseus Arm or the Scutum Centaurus Arm. Instead, the Orion Arm is a minor spur branching off between the larger arms, almost like a side street, rather than a major highway in the galactic layout. Even though it is not the brightest or most impressive part of the galaxy, this region is stable enough for stars like the Sun to form and evolve without major disruptions from supernova clusters or dense molecular clouds. That stability matters because the Sun completes one full orbit around the Milky Way every 230 million years, carrying Earth and its planets with it through different galactic neighborhoods. Everything on Earth, from the oceans to the atmosphere to the evolution of life, has taken place during a single orbit around the galactic center. What keeps all these stars moving in their paths is gravity, but not just the gravity of visible objects. When astronomers measured the rotation speed of the Milky Way, they expected stars farther from the center to move more slowly, the same way planets farther from the Sun orbit more slowly. Instead, they found that stars throughout the disk orbit at nearly the same speed, a clear sign that something unseen provides enormous gravitational pull. That unseen something is dark matter, and its gravitational field surrounds the galaxy in a giant envelope that holds everything together. If the Milky Way were only made of the matter we can see, stars, gas clouds, dust lanes, the galaxy would not rotate the way it does. Stars on the outer edges would fly off into space because there would not be enough central mass to keep them bound. But dark matter's gravitational influence prevents this from happening. It anchors the galaxy and shapes the motion of every star, even though no telescope can see it directly. This invisible structure has been studied in detail through decades of observation. The Hubble Space Telescope helped uncover the distribution of dark matter in the halo by tracking the bending of light around galaxies and comparing it to mass that could be measured. Meanwhile, surveys like the Sloan Digital Sky Survey mapped large areas of the Milky Way, revealing stellar streams formed by the remains of ancient galaxies absorbed by the Milky Way's gravity. These streams act like fossils, recording the history of the galaxy's growth. Gaia, the European Space Agency's astrometry mission, has taken this work even further by measuring the motions of more than 1 billion stars with extreme precision. Thanks to Gaia, astronomers created detailed 3D maps of the disk and discovered ripples, waves, and warps in its structure. These distortions showed that the Milky Way is not a calm, flat disk, but a dynamic system being shaped by past collisions, gravitational interactions, and the motion of dark matter around it. With these observations, scientists have begun to build a picture of the Milky Way's internal movement. The Sun travels around the galaxy at about 220 kilometers per second, fast enough to cross the distance from New York to Los Angeles in 20 seconds. Nearby stars share similar speeds, so from the perspective of the solar system, the motion feels smooth. But across the entire galaxy, these motions form a grand rotating system. Gas clouds orbit in the disk, spiral arms shift over millions of years, and stars migrate inward or outward depending on gravitational interactions. A star like the Sun might form at one location, but drift several thousand light years over its lifetime. Understanding these dynamics helps reveal how the galaxy evolves, how star formation changes with time, and how the environment around the solar system may shift in the future. At the center of the Milky Way sits a region unlike anything near the solar system, Sagittarius. A star, the supermassive black hole, anchors the entire galaxy with a mass about 4 million times that of the Sun. There is no danger of the Sun being pulled in because it sits too far away and is held in place by the combined gravity of billions of stars. But Sagittarius A* influences the motion of everything closer to the core. The center is crowded with stars packed much more densely than in our region, and many of these stars orbit the black hole at speeds that demonstrate its enormous mass. Observations of stars like S2, which completes its orbit in a little over 16 years, helped confirm the presence of a supermassive black hole long before direct evidence was captured. Infrared telescopes, radio arrays, and eventually the Event Horizon Telescope revealed the glowing region around Sagittarius A*, showing the gas swirling in intense gravitational fields. Life in the outer parts of the galaxy is very different from life near the center. The density of stars near the core increases exposure to radiation and gravitational disturbances, while the region around the Sun provides a quieter zone. This contrast has shaped theories about where planets with life can exist. Too close to the center and the environment becomes hostile. Too far away and star formation decreases, reducing the chances of finding rocky planets at all. The Sun's position in the Orion Arm places it in a region that may be ideal for long-term stability, though many stars share similar environments. Understanding this distribution helps scientists judge where future telescopes might search for planets in stable orbits. For centuries, people assumed the Milky Way was the entire universe because it was impossible to see beyond it with early instruments. The structure became clearer only when astronomers used telescopes powerful enough to resolve individual stars in nearby galaxies. Edwin Hubble's work in the 1920s showed that many fuzzy patches of light were not clouds in the Milky Way, but other galaxies far beyond it. This discovery changed the way scientists viewed our place in the universe. Instead of a unique or central system, the Milky Way became one of trillions of galaxies, each with its own structures and histories. But mapping our own galaxy remained a challenge because we observe it from inside the disk. Dust clouds block distant regions, especially when looking toward the center, so astronomers rely on infrared, radio, and X-ray wavelengths to see through the dust and gather information about the hidden parts. As technology advanced, missions like Gaia, Hubble, Kepler, Chandra, and the James Webb Space Telescope provided tools for filling in the gaps. Gaia's precise measurements allow scientists to reconstruct the Milky Way's shape, including the slight warp that makes the disk bend upward on one side and downward on the other. This warp likely comes from gravitational interactions with satellite galaxies, like the Large Magellanic Cloud, or from uneven distribution of dark matter in the halo. Studying these effects reveals not only the structure of the Milky Way, but also the dynamics of galaxy formation in general. The Milky Way's halo is another area of active research. Though faint, it contains some of the oldest stars in the galaxy, many of them formed before the disk took shape. These stars hold clues about the environment of the early universe, and their chemical signatures reveal information about the first generations of stars. The halo also contains streams of stars from small galaxies that have been absorbed. These stellar streams curve across the sky in long arcs, showing where the Milky Way has torn smaller systems apart through tidal forces. Astronomers have discovered dozens of such streams in recent years, and Gaia's data continues to reveal new ones. Each stream helps reconstruct the Milky Way's history, allowing scientists to trace how it grew through mergers and how its dark matter halo is shaped. The concept of galactic escape velocity also becomes important when studying the Milky Way's gravitational structure. For an object to leave the galaxy entirely, it must reach a speed of more than 500 kilometers per second near the Sun's location. This speed increases when approaching the center and decreases near the edges. But the requirement shows how powerful the Milky Way's gravity is. Most stars will remain bound for billions of years because only extreme events like supernova explosions or close encounters with massive objects can accelerate them to escape speeds. Some stars, known as hypervelocity stars, have been observed moving fast enough to leave the galaxy. Many of these stars were flung outward after interacting with Sagittarius A star, showing how the black hole can act like a slingshot under certain conditions. As observations improve, scientists continue to refine the picture of the Milky Way's motion through the universe. The galaxy is not stationary. It moves through space at hundreds of kilometers per second, interacting with nearby galaxies in the local group. The Andromeda Galaxy, for example, is on a long-term collision course with the Milky Way. Though the event is billions of years in the future, the gravitational pull between the two galaxies already influences their motion. Studies using Hubble and Gaia data have helped estimate the timing and shape of the eventual merger, showing that galaxy collisions are part of the natural life cycle of the universe. These mergers do not destroy most stars because the distances between stars are so vast, but they dramatically reshape the structure of the galaxies involved. The Milky Way's spiral structure is another area where observations and simulations combine. Spiral arms are not fixed objects. They are patterns created by density waves moving through the disk. As gas clouds enter these waves, they compress and form new stars. When these stars move out of the wave, they drift into regions between the arms. This process creates the bright, star-filled arms that define the galaxy's appearance. Understanding these density waves helps explain the rhythm of star formation across the disk and why certain regions produce more new stars than others. The motion of these waves also interacts with the Sun's orbit, which means the solar system may pass through different density environments over time. Observations from missions like Herschel and Spitzer reveal the fine structure of the gas and dust in the arms, showing how molecular clouds collapse into clusters and how supernova explosions shape the surrounding medium. These processes feed back into the galaxy's evolution, recycling material and creating patterns that spread across thousands of light years. The Milky Way becomes not just a static structure, but a living environment where birth, decay and motion happen on scales far beyond a human lifespan. As scientists build 3D models of the Milky Way using Gaia and radio mapping of hydrogen gas, A detailed picture of the disk's thickness has emerged. The thin disk contains young stars and regions of active star formation, while the thick disk contains older stars with different chemical compositions. By comparing these populations, researchers can track how the galaxy changed over billions of years. The thick disk may have formed through early mergers or internal processes that pumped stars to higher altitudes. Understanding the difference between these disks helps scientists interpret the chemical evolution of the galaxy and reveals where elements necessary for life originated. Newer telescopes continue to push this work forward. Radio arrays like ALMA and the Very Large Array provide detailed views of cold gas in the spiral arms. Infrared observations show regions hidden from optical telescopes. Spectroscopy allows scientists to measure the chemical composition of stars and gas clouds, revealing how material cycles through generations of star formation. This combination of tools makes the Milky Way one of the best-studied galaxies in the universe, even though seeing its full structure requires indirect methods. The movement of stars in the disk creates patterns that can be mapped using Gaia's data. Some stars follow smooth circular paths, while others oscillate vertically through the disk or shift radially over time. These motions reveal gravitational interactions with spiral arms, the central bar, and dark matter substructures in the halo. Some ripples in the disk may have been caused by past encounters with dwarf galaxies, while others appear to be linked to internal resonances. By studying these motions, scientists gain insight into the unseen mass in the galaxy and the long-term evolution of the disk. Galactic rotation also highlights the role of gravity at large scales. The Sun's orbit shows that the Milky Way is stable enough to hold stars in predictable paths for billions of years, but the underlying cause of this stability remains partly mysterious, because dark matter plays such a large role. Research using gravitational lensing and simulations suggests that dark matter may form a roughly spherical halo, though its exact shape is difficult to determine. This halo influences how the galaxy moves through the universe and how it interacts with nearby galaxies. The Milky Way's past is filled with collisions. Evidence shows that the galaxy absorbed several dwarf galaxies, including the Gaia Enceladus system, whose stars now make up much of the thick disk and inner halo. Other remnants, like the Sagittarius dwarf galaxy, continue to orbit and gradually break apart. These ongoing interactions leave trails of stars that stretch across the sky. Mapping these streams helps scientists reconstruct the Milky Way's growth and refine models of dark matter distribution. The more streams they map, the clearer the picture becomes of how the galaxy has evolved and how it will change in the future. The distribution of gas in the Milky Way also plays a major role in shaping its structure. Hydrogen gas fills much of the disk, and radio telescopes map this gas to understand the shape of the spiral arms and the warp in the outer disk. The hydrogen disk extends far beyond the visible star-filled region, tracing the gravitational influence of the halo. This extended gas layer shows how the galaxy interacts with the intergalactic medium and how material flows in and out of the disk. Star formation regions provide insight into processes happening on smaller scales. In areas like the Orion Nebula, scientists observe massive young stars forming inside dense clouds. These regions show how gravity gathers gas into clusters and how radiation from newborn stars shapes their surroundings. Studying these processes helps scientists understand how the Sun formed and how similar stars evolve. Because the solar system sits inside the Orion arm, many of these regions are close enough to observe in detail. Scientists are using numerical simulations to model the Milky Way's evolution. These models incorporate physics governing gravity, gas dynamics, star formation, and feedback from supernovae. Simulations reveal how spiral arms form, how the bar at the center rotates, and how the disk responds to external perturbations. By comparing simulations to observations, researchers refine their understanding of the galaxy's past and future. The Milky Way's movement through space is influenced by large-scale structures in the universe. It and the Andromeda Galaxy move toward a gravitational anomaly known as the Great Attractor, a region containing massive galaxy clusters and unseen mass. This pull is part of the larger motion of the local group toward even bigger structures like the Shapley supercluster. These motions occur on scales that challenge human intuition, showing how the Milky Way fits into the cosmic web. Understanding the Milky Way reveals humanity's true address in the universe. Every star in the night sky is part of the same rotating disk, sharing the same long journey around the galactic center. The gravity that shapes our orbits extends across immense distances, connecting billions of stars into a single structure. The dark matter halo reaches far beyond anything visible, wrapping the galaxy in an invisible gravitational field that determines how it spins and how it interacts with its surroundings. Observations from missions like Hubble, Gaia, and radio surveys continue to deepen this understanding, showing that the Milky Way is not just a backdrop to the night sky, but an active, dynamic system evolving over billions of years. Galactic gravity, the ultimate cage. Gravity on Earth feels gentle. People walk, jump, stumble, climb stairs, run, fall, and rise again, without ever stopping to think about the force holding everything to the ground. That familiar pull hides a deeper reality stretching across distances far beyond the solar system. Gravity links stars, planets, moons, gas clouds, and dark matter into one enormous structure that holds everything in place inside the Milky Way. This force is not loud or dramatic. It works silently, gripping every particle with a strength that never weakens or turns off. The Milky Way is not just a collection of stars. It is a cage built from gravity, and every object inside it remains trapped unless it reaches a speed so extreme that only very rare events can produce it. The Milky Way contains hundreds of billions of stars, giant reservoirs of gas, swirling clouds of dust, and a huge amount of dark matter that surrounds everything in a sprawling halo. Every star pulls on every other star. Every gas cloud pulls on every other cloud. Every planet, every comet, every asteroid, every drifting rock or icy grain floating in the dark feels the collective grip of this enormous system. Gravity on this scale behaves like a net that stretches across 100,000 light years, holding the disk together and shaping the motion of every object inside this colossal rotating structure. Even the fastest spacecraft launched from Earth cannot outrun it. Escape velocity near the Sun's position in the galaxy ranges from 500 to 600 kilometers per second. That speed is not a suggestion, it is a hard requirement. Anything below that limit sinks forever into the Milky Way's gravitational field. That might sound like an arbitrary number, but it comes from the combined mass of hundreds of billions of stars plus the invisible mass of the dark matter halo. The Sun sits roughly 27,000 light-years from the galactic center, far from the region where gravity from the central black hole dominates. Even at this distance, the pull remains extremely strong because of the enormous mass spread through the disk and halo. The speed requirement climbs higher near the galactic center, where stars pack more tightly and where Sagittarius A*, the supermassive black hole, anchors everything. The escape speed in that region becomes far greater than anything near the Sun. Nothing produced through normal star formation or normal stellar motion can reach that limit. Only extreme events, such extreme collisions, violent gravitational encounters, or interactions with Sagittarius A*, give anything a chance of breaking free. When people talk about escape velocity, they often think about rockets leaving Earth. Earth requires a little more than 11 kilometers per second for a spacecraft to leave its gravitational hold. The solar system requires roughly 42 kilometers per second to leave the Sun's influence from Earth's distance. People can imagine those speeds because rockets and probes approach them. When the Voyager probes left Earth, they reached speeds near 17 kilometers per second, the fastest long-term cruise speed ever achieved for explorers launched from this planet. That speed is enough to leave the solar system eventually, but it is nothing compared to what the Milky Way demands. The Parker Solar Probe is the fastest human-made object ever created. Its mission brings it extremely close to the Sun, where intense gravitational acceleration increases its speed to nearly 200 kilometers per second. That number looks impressive. It is an achievement that required generations of study, engineering, and planning. Still, even that incredible speed is nowhere near enough to escape the galaxy's pull. 200 kilometers per second sounds fast, yet it remains less than half the minimum needed for escape from the Sun's region. It falls far below the speeds of stars moving near the galactic center. The galaxy's grip stays firm, even on the fastest machine humans ever launched. People sometimes imagine future spacecraft with engines far stronger than anything on Earth today. Those ideas usually involve fusion drives, antimatter thrusters, or exotic propulsion concepts that push the limits of physics. Even if a future craft reached 1,000 kilometers per second, it would still struggle to escape the Milky Way unless it launched in a region with very low gravitational influence. The galaxy is simply too massive. Its structure creates a gravitational well so deep that almost nothing can climb out of it under normal circumstances. The only objects known to break free are hypervelocity stars. These stars move at speeds greater than the required escape velocity. Some of them travel so fast that they will drift out of the Milky Way completely and wander through intergalactic space forever. Hypervelocity stars are rare and violent events produce them. One common source involves a close encounter with Sagittarius A*. When a binary star system enters the region near the black hole, gravity tears the system apart. One star falls inward toward the black hole and spirals into its gravitational sink. The other star receives a violent kick that launches it outward at tremendous speed. That kick can accelerate it above the escape limit, turning it into a runaway star that leaves the galaxy behind. Another possible source involves collisions with other stars or encounters with extremely dense clusters. When stars in such clusters interact, gravitational slingshot effects can accelerate one star while decelerating another. In most cases, the speeds remain below galactic escape levels. Occasionally, the right alignment delivers a huge acceleration. That rare event propels the star through the disk at speeds no normal orbit could produce. Once the star reaches the outer regions of the halo, it continues traveling until it enters the nearly empty expanse that lies between galaxies. Nothing stops it. Nothing slows it. It drifts into the intergalactic void, where distances between galaxies stretch for millions of light years. Even though hypervelocity stars can leave the Milky Way, spacecraft travel remains extremely limited. Voyager 1, the most distant spacecraft humanity ever launched, moves through the outer edge of the solar system at a slow crawl compared to galactic motions. Nothing on Voyager 1 can accelerate it further. It has no fuel for enormous speed boosts. It has no engine capable of fighting the galaxy's gravity. It looks heroic in human terms because it passed the boundary where the sun's wind stops dominating space, yet it remains trapped inside the galactic cage. It will orbit the galaxy for millions of years unless a rare encounter with something massive changes its path. Even then, the odds remain incredibly low. The gap between human spacecraft and galactic escape velocity shows the enormous scale difference between local space travel and galactic movement. People can launch probes to Jupiter, Saturn, Pluto, or interstellar space with careful use of gravitational assists, but those maneuvers barely scratch the surface of the Milky Way's gravitational requirements. Gravity from the galaxy acts everywhere and in every direction, creating a constant downward slope from which nothing can climb without extraordinary speed. This cage does not feel rigid. It does not block movement through normal space. The solar system floats through the disk along its orbit, carrying Earth on a giant circular path lasting hundreds of millions of years. The cage does not restrict drifting or rotation. It restricts escape. The sun, the planets, comets, dust, and everything else in the solar system travel around the galaxy without breaking free. Their speeds match the rotation of the surrounding region. That smooth motion creates the illusion of freedom. Nothing about it feels trapped because nothing attempts to break loose. Only when humans compare spacecraft speeds to the escape limit does the true scale of the cage become clear. Gravity within the Milky Way also shapes how stars drift across the disk. Stars follow curved paths around the center, but they also bob slightly up and down through the galactic plane. These motions come from the pull of the disk's mass. A star moving above the plane feels a downward pull. A star below the plane feels an upward pull. Over millions of years, those motions create gentle oscillations. Even these oscillations remain under the control of the galaxy's gravity, unable to send any star into free space unless an outside force intervenes. Dark matter strengthens the cage even further. Although invisible, it dominates the mass of the halo and helps maintain the rotation speed of the disk. Without dark matter, the outer parts of the Milky Way would rotate at slower speeds, and the disk would not hold its shape. The stars near the sun would drift outward until the whole structure loosened. Instead, the dark matter halo keeps everything bound. Its influence does not produce light or heat. It produces gravity, and that gravity increases the escape speed far beyond what visible matter alone would create. Because dark matter surrounds the galaxy in an enormous halo that extends far beyond the visible disk, even objects at the outer edge remain trapped. A spacecraft reaching that region would not find an easy exit path. The halo's gravitational reach stretches hundreds of thousands of light years. That region contains old stars, stellar streams left from ancient collisions, and extremely faint structures that reveal the history of the Milky Way's growth. All of these objects move under the influence of both visible mass and dark matter. Their motions reveal how deep the gravitational well extends. Even stars far from the center orbit at high speeds because the halo provides a powerful gravitational anchor. Escape from that anchor demands incredible velocity. Hypervelocity stars achieve it through violent gravitational events. No natural process in the solar system produces anything close. The Sun cannot launch a planet or asteroid at escape velocity. Jupiter cannot fling a moon into intergalactic space. No comet gains enough energy during its orbit. Even supernova explosions near the solar system would fall short of launching matter at the required speed. Only the environment near a supermassive black hole delivers the right combination of forces. Human technology remains nowhere near that scale. Even the most ambitious propulsion concepts still rely on slow acceleration. Interstellar travel ideas often involve acceleration so gentle that the craft would need decades or centuries to reach significant fractions of light speed. Those speeds would carry a ship to nearby stars eventually, but they still fall far below the escape speed of the galaxy. A craft traveling at 10% of light speed would still not reach the galactic limit. That shortfall illustrates the sheer depth of the Milky Way's gravitational well. Only a small group of stars achieve the required speed, and only through violent events in extreme environments. The Milky Way's gravity cage does not only trap stars and spacecraft, it traps light in a limited sense. Light moves at the universal speed limit, so gravity cannot hold it the way it holds matter. Yet light bends around massive objects. The galaxy's total mass bends light slightly, creating lensing effects that allow astronomers to map the distribution of dark matter. Although light always moves forward, the path it takes reveals the shape of the gravitational field that surrounds it. That field extends through the disk, into the halo, and out into the intergalactic medium. Even photons curve gently through this space under the influence of gravity. This does not trap the light. Instead, it reveals the cage's boundaries and shape. The deeper the view into the Milky Way, the stronger the gravitational influence. Stars toward the center move in tight orbits. Dust clouds swirl around the core. The environment near Sagittarius A** becomes chaotic because the gravitational forces increase at every step inward. That region produces some of the fastest stars in the galaxy, although most remain bound. Only the most extreme events send anything outward at escape speed. Researchers discovered several hypervelocity stars traveling outward through the halo. Some move at speeds near 1,000 kilometers per second. Their high speeds reveal that they passed extremely close to Sagittarius A*, or encountered a massive object that accelerated them during a complicated three-body interaction. These interactions occur when two stars orbit each other, while a third object, usually very massive, disrupts their orbit. The energy exchange can launch one star outward and tighten the orbit of the other two. Only a tiny fraction of these events reach escape velocity. The existence of hypervelocity stars proves that escape is possible, but the rarity highlights how strong the Milky Way's gravitational field remains. Most stars stay bound for billions of years. The Sun will remain bound until it dies. It will orbit the galaxy, roughly one full cycle, every 230 million years. During its lifetime, it will complete about 20 orbits. Nothing in its environment will give it the speed needed to escape. Even if the solar system experienced a close encounter with another star, the gravitational effects would likely disturb planetary orbits without delivering the enormous acceleration required for escape. Spacecraft traveling through the galaxy share the Sun's fate. They drift along in their own small orbits, following the solar system's path around the center. They never gain enough energy to climb out of the galaxy's gravitational well. The galaxy's motion carries them forward, but their individual velocities do not change the large-scale picture. They remain trapped in the same cage that holds everything from gas clouds to globular clusters. Galactic gravity creates long-term stability for the disk. It prevents stars from drifting away into the intergalactic void. It binds globular clusters and satellite galaxies into orbits. It shapes the paths of stellar streams from ancient collisions. It maintains the structure of spiral arms through density waves. It keeps the galaxy rotating at a steady pace. This gravitational cage controls every motion inside the Milky Way, forming a cosmic environment where everything is locked into place on a scale larger than anything people encounter on Earth. Even though this cage sounds restrictive, it creates the environment that allowed the solar system to exist in the first place. Gravity gathered gas into the molecular cloud that formed the Sun. It held the solar nebula together long enough for planets to grow. It stabilized Earth's orbit around the Sun. It guided the solar system along its path through the galaxy. Without the galaxy's gravitational cage, the solar system would never have taken shape. Gravity holds everything together, from the smallest dust grains to the largest clusters of stars. When people look at the night sky from Earth, they see pinpoints of light scattered everywhere. Those stars appear still, but every one of them moves through the galaxy along a curved path, created through the combined gravity of the Milky Way's mass. The cage is not visible in the sky. It reveals itself through motion, orbit, and speed. Everything drifts inside its boundary, yet nothing escapes without an extraordinary push from forces far more powerful than anything humans control. Distances to other galaxies, light years, and the void. The moment the mind leaves the comfort of the Milky Way and begins to think about the space between galaxies, everything familiar begins to fade. The scale changes so violently that normal reference points collapse. Inside a galaxy, stars may feel incredibly far away. Proxima Centauri sits more than 4 light-years from Earth, and that number already sounds impossible for a traveler. Yet that gap is nothing compared to the yawning gulf that stretches from the Milky Way toward the next great island of stars. The nearest major galaxy to us, Andromeda, waits 2.537 million light-years away. That number stands there with no mercy and no attempt to soften its meaning. Light, the fastest thing known, takes more than 2 million years to travel that road. A spacecraft carrying humans would crawl through that space for longer than humanity has existed. Looking across intergalactic distances forces a new kind of thinking. Light years are not an attempt to sound dramatic. They are units created because normal units fail immediately. A kilometer holds meaning when talking about mountains or oceans. Even thousands of kilometers make sense when discussing Earth. 1,000,000 kilometers begin to drift into an abstract place, yet remain manageable with enough imagination. A light year, however, is so large that it strips away everything familiar. It measures the distance light covers in one full year, moving non-stop at nearly 300,000 kilometers every second. When that number is multiplied millions of times, the gap between galaxies becomes something cold and detached from anything related to human life. Human timescales make this even more strange. A lifetime usually stays below 1 century. Civilizations rise and fall in a few thousand years. Recorded history holds only around 6,000 years of stories. The entire existence of Homo sapiens sits near 300,000 years. This entire stretch of time is shorter than the amount of time light needs to cross the distance between the Milky Way and Andromeda. A beam released when early humans hunted with stone tools would still be traveling through the void right now, still moving in a straight line through silence, still unbothered by anything, still far from reaching the next galaxy. That comparison turns intergalactic travel into something unreal. Space does not care about human calendars. It keeps its distances set with ancient, indifferent precision. Astronomers learned Andromeda's distance through years of observations. The galaxy looks like a faint smudge to the naked eye under dark skies. Telescopes reveal swirling arms, dust lanes, and a bright central region, a structure echoing the Milky Way's design. Cepheid variable stars inside Andromeda allowed astronomers to measure its true scale. Once they realized the brightness pulse of those stars followed reliable patterns, they could calculate their actual luminosity. Their faint glow from Earth revealed a shocking truth. The galaxy must sit millions of light years away. This discovery shattered the belief that the Milky Way held the entire universe. Suddenly, the cosmos expanded. The distances became monstrous. When modern measurements refined Andromeda's position to 2.537 million light-years, the number became the anchor for every conversation about the gulf between galaxies. It is the closest spiral galaxy to us and still far beyond any hope of travel. If the closest major neighbor is that far, the next galaxies stretch even more. The The Triangulum galaxy sits beyond Andromeda. The Virgo cluster spreads across tens of millions of light-years. The Coma cluster reaches hundreds of millions. The light that brings their image to Earth started its journey before humans, before mammals, before many species of dinosaur existed. That light traveled across time so long that Earth's continents shifted while it crossed empty space. The void between galaxies holds almost nothing. Inside the Milky Way, space between stars contains gas atoms, dust, radiation, and magnetic fields. Even that thin substance becomes dense compared to the deserts between galaxies. Intergalactic space contains fewer particles per cubic meter than the best laboratory vacuums ever created. A traveler leaving the Milky Way would enter a place so empty that a single hydrogen atom may drift for kilometers with no neighbor. This emptiness stretches so far that entire lives, nations, and civilizations could rise and vanish without changing anything in that silent ocean. Comparing human timescales to these distances creates a sense of limits that cannot be escaped. A commercial airplane moves at less than 1,000 kilometers per hour. A spacecraft in Earth orbit reaches around 28,000 kilometers per hour. Voyager 1, the fastest human-made object leaving the solar system, travels near 17 kilometers every second. That pace is incredible near planets and moons, yet nothing against intergalactic distances. At that speed, Voyager would need many tens of billions of years to reach Andromeda, long after stars fade and galaxies lose their energy. That timeline dwarfs human existence so heavily that human travel becomes irrelevant on an intergalactic scale. Even the Parker Solar Probe, which reaches stunning speeds near the Sun and becomes the fastest object ever created at more than 600,000 kilometers per hour, still turns into a slow crawler in the context of millions of light-years. The numbers crush any hope for physical travel. The universe set its distances on a scale designed for light, not biology. A spaceship would need propulsion far beyond anything tested before. It would need to reach fractions of light speed and sustain that pace for centuries. This means generations born and lost inside a small craft, drifting through emptiness with no chance of turning around. And even that scenario fails when dealing with millions of light years. The void between galaxies also blocks communication. Signals move at light speed. A message sent from the Milky Way toward Andromeda would arrive more than 2 million years later. A reply would take the same amount of time. This makes intergalactic conversation physically impossible. Even a radio broadcast from Earth right now is spreading into space, but will live inside the void with no expectation of reaching listeners. The strength decreases with distance. After a few thousand light years, the signal blends with cosmic noise. After millions, it disappears into the background. No technology can fix that. The physics remains fixed, indifferent to human desire. The comparison between Earth's timescales and galactic distances becomes even sharper when looking at stellar evolution. Stars live for millions to billions of years. A star like the Sun shines for roughly 10 billion years. Massive stars burn out in only a few million. Dwarfs may last trillions of years. These life cycles stretch longer than the time light needs to move between galaxies. Human lifetimes, sitting near 80 years, exist like flashes inside these enormous periods. Even entire civilizations look like quick sparks. While humans study galaxies, stars inside those galaxies move through their own lifespans, explode, collapse, or drift quietly through space. When astronomers observe Andromeda, they do not see its present form. They see light released more than 2 million years ago. The galaxy could already have changed, though the changes may not be dramatic on that timescale. The concept of look-back time means that deep space functions like a cosmic archive. Everything seen from Earth is ancient. The further the light traveled, the older the image becomes. Galaxies at the edge of what telescopes detect show light that left when the universe was young and dense. Those galaxies may no longer exist in the same form. Humanity witnesses their past states from a safe distance, while the present remains invisible. Comparing human timescales to these distances highlights the limits of human biology. A human heart beats near 100,000 times per day. A child grows into an adult in less than 2 decades. Generations change within a century. These rhythms collapse when placed next to galactic movement. The Milky Way rotates once every 230 million years. Earth completes that journey without any living organism tracking the entire cycle. Dinosaurs saw the galaxy in a different orientation than humans see today. When Earth began its previous galactic rotation, The earliest mammals crawled unnoticed through forests. When discussing intergalactic distances, those rhythms expand even more. A star traveling through the Milky Way moves at hundreds of kilometers per second. That speed helps it orbit the galactic center. Yet no star in the galaxy moves fast enough to leap across the void toward Andromeda. Only hypervelocity stars have that potential, and even those are rare accidents, usually flung from near the central supermassive black hole. They move so quickly that they exceed the escape speed of the Milky Way, but their journey through intergalactic space takes longer than human existence. The star travels in a straight line through darkness, nearly devoid of matter, with no guarantee of reaching another galaxy. It becomes a lone traveler drifting through the deepest emptiness known. The separation between galaxies also shapes cosmic structure. Galaxies form clusters held together through gravity. The local group holds the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of dwarf galaxies. The void around this group stretches so far that each cluster becomes an island. Between clusters, matter becomes even more rare. These gaps extend for tens of millions of light years. Observations show long filaments connecting groups of galaxies, forming a web across the universe. Yet the strands of that web still contain unimaginable gaps, filled with almost nothing. Thinking about intergalactic space invites questions about movement. Everything in the universe moves. Galaxies drift through space. Andromeda approaches the Milky Way at more than 100 kilometers per second. That sounds fast, yet it still needs billions of years before the two galaxies meet. A speed like that turns into a slow crawl when the distance covers millions of light years. Human senses are not built to grasp movement on that scale. A car moving at 100 kilometers per hour feels fast. A spacecraft moving at more than 30,000 kilometers per hour feels extreme. Yet nothing built so far even begins to touch the speeds needed for intergalactic travel within meaningful time. This scale also reveals how small human presence is. Earth occupies a location inside a single spiral arm of a mid-sized galaxy. The galaxy floats inside a small cluster near the edge of a cosmic filament. That filament sits inside a foam-like structure that fills the universe. Human life exists inside one tiny corner of this structure. No matter how advanced technology becomes, intergalactic travel remains a challenge set at the highest possible difficulty. Not because of obstacles that block the road, but because the road stretches so far that no realistic propulsion approach can shorten the trip. Astronomers use standard candles, redshift measurements, and parallax techniques to map galactic distances. Each method builds a ladder that reaches further into space. Parallax handles nearby stars. Cepheids handle distant stars and nearby galaxies. Type a supernovae handle far galaxies. Redshift handles everything stretching across the universe. These tools show a map where galaxies retreat from Earth due to cosmic expansion. The farther the galaxy, the faster it appears to move away. This expansion complicates intergalactic travel even more. The space between galaxies stretches. A traveler heading toward a distant galaxy must fight against that expansion. In most directions, the retreating motion of the universe eventually outpaces even a beam of light. Those galaxies move beyond reach. This reveals another harsh truth about intergalactic distances. Not only are they large, they are growing. Andromeda is one of the few exceptions, because gravity inside the local group overpowers expansion and pulls the Milky Way and Andromeda together. Many other galaxies move away so quickly that their light will never reach Earth again. The universe allows a limited horizon for observations. Beyond that horizon, galaxies vanish from view forever. No spacecraft could reach those galaxies because the expansion rate overpowers any possible travel speed. They slip into permanent darkness relative to Earth. This creates a universe where human exploration exists inside a shrinking window defined through cosmic motion. When talking about intergalactic distances, it becomes clear how disconnected human timescales are from cosmic events. A second feels short. A minute feels manageable. Hours shape the rhythm of work and rest. Days track the rotation of Earth. Months track the orbit of the Moon. Years track the orbit of Earth around the Sun. Everything familiar follows cycles measured in years or decades. Intergalactic travel needs timelines that stretch beyond civilizations and perhaps beyond species. It demands patience no living organism can possess. Astronomers examining the void between galaxies use sophisticated instruments. Space telescopes measure faint background radiation, ghostly streams of gas, and intergalactic magnetic fields. The emptiness is not perfect, but it is close. Photons travel through the void with almost no interruptions. Even dust grains become rare treasures. Cosmic rays shoot through that space with nothing to block them. A spacecraft drifting through that environment would face constant radiation exposure, but it would not encounter many atoms. The vacuum becomes a silent arena where only gravity and light make noticeable changes. The separation between galaxies also creates isolation. The Milky Way's stars sit close enough to give travelers constant targets. A journey to a nearby star system remains difficult but meaningful. The vacuum between galaxies removes that pattern. A traveler leaving the Milky Way would soon reach a region with no visible stars. Only faint light from distant galaxies would remain. The darkness would appear almost absolute. A long journey through that region would become a journey through pure emptiness, with no checkpoints, no markers, no places to stop, and no landmarks to guide the path. Even the sense of direction becomes abstract. Intergalactic distances also influence the energy necessary for escape. To leave Earth, a spacecraft needs to reach escape velocity near 11 kilometers per second. To escape the Sun, it needs more than 40 kilometers per second. To escape the Milky Way, the speed near the Sun's location must reach around 500 to 600 kilometers per second. These speeds become milestones for travel within the galaxy. Yet none of those numbers approach the speeds required for meaningful intergalactic movement. Galactic gravity holds stars in place, and that gravitational cage extends far into the halo. Escaping from that cage already pushes the limits of propulsion. Beyond that escape, the void remains so vast that the journey becomes essentially permanent. The gap between galaxies also shapes the fate of light. A photon released inside a galaxy may collide with dust or gas. A photon released into intergalactic space travels freely, losing energy due to cosmic expansion and redshifting into lower frequencies. Light from early galaxies stretches into infrared wavelengths by the time it reaches telescopes. This redshift helps measure distance. Higher redshift means greater distance. Eventually, the redshift becomes so extreme that the galaxy fades from detection. It becomes lost in the darkness of the cosmic horizon. Intergalactic distances make everything about the universe feel older. Light from Andromeda reveals a galaxy as it existed more than 2 million years ago. Light from galaxies in the Virgo cluster shows events that happened 60 million years ago. When that light started its journey, dinosaurs still roamed Earth. Light from galaxies near the edge of the observable universe reveals events from more than 13 billion years ago. That light began its journey when the universe was young, dense, and filled with early stars. Observing that light gives humanity a chance to look backward in time, though the present state of those galaxies remains hidden. Human timescales cannot adjust to these distances. The universe sends ancient messages through light. Telescopes decode them, yet nothing can accelerate the time it takes for new information to arrive. A supernova in a distant galaxy may have exploded millions of years ago, though the light reaches Earth only now. A collision between galaxies may have happened long before Earth formed, though humans view the aftermath through telescopes today. Intergalactic space freezes events in time. The messages from those events drift across the void like whispers from ancient eras. When future missions attempt to explore further regions of the Milky Way, the contrast with intergalactic distances will become even more clear. A probe could travel to nearby stars within centuries. A fusion-powered spacecraft or future propulsion breakthrough may shorten that trip. Yet no propulsion design so far reaches anywhere near the scale needed for intergalactic exploration. Even light sails driven through laser arrays, a popular futuristic concept, face limits. They may reach a fraction of light speed, enough to explore within the galaxy. However, millions of light years still remain unreachable within human timelines. The void between galaxies shapes astronomy, physics, and dreams of exploration. The distances force scientists to study the universe from afar. Humans rely on telescopes, observatories, and detectors to read signals across enormous stretches of space. These signals allow mapping of galaxy clusters, filament structures, and cosmic evolution. Observations help reveal how galaxies collide, merge, age, and drift. Yet everything remains at a distance. No probe has ever left the Milky Way, No probe comes close to touching intergalactic space. Humanity watches these regions from the edge of a spiral arm, using light instead of travel. Andromeda's enormous distance remains the most relatable example of the void between galaxies. 2.537 million light-years stands without compromise. It tells a story of scale that does not bend to human preference. It remains a fixed measure created through cosmic structure. That distance dwarfs human timelines, cultures, and ambitions. It turns the nearest major galaxy into a neighbor that cannot be reached through any practical method. Even though Andromeda moves toward the Milky Way, the collision sits billions of years in the future. That event will reshape both galaxies, forming a giant elliptical structure. Stars will rise and fall during that long wait. Entire species may rise and vanish. Planetary systems may shift. Earth may experience changes far more dramatic than anything in recorded history. Yet the galaxies continue their slow drift toward each other, unaffected through human timescales. Focusing on intergalactic distances reveals a universe built on a scale that dwarfs every human frame of reference. Galaxies float through dark oceans so wide that even light struggles to reach across them. Time stretches into millions and billions of years. Human lives flicker inside that vastness with no impact on the cosmic landscape. The gulf between the Milky Way and Andromeda represents only the first step into that wilderness. Beyond it, the void expands with no end in sight, filled with clusters, superclusters, filaments, and unimaginable gaps where no traveler has ever moved. The universe holds its structure in silence, indifferent to the small creatures who look upward and try to measure distances that exceed their own existence. The separation between galaxies remains one of the greatest barriers in all of physics. It defines the limits of exploration. It defines the limits of communication. It defines the limits of speed. It defines the boundaries within which human life unfolds. And through everything, that number remains in place. 2.537 million light-years from here to Andromeda. It stands as the simplest, clearest demonstration of the void between galaxies, a reminder of the immense scale that surrounds the Milky Way, a scale that stretches beyond imagination, beyond biology, and beyond. Light does not cheat. It travels at one speed and one speed only, and nothing in the universe outruns it. Light from a galaxy 10 million light-years away took 10 million years to reach Earth. Light from a galaxy 1 billion light-years away left long before Earth ever formed. Light reaching telescopes from the oldest regions of the observable cosmos departed during an era when no stars existed, no planets existed, no heavy elements existed, and no structure filled the void. When astronomers point large instruments toward the faintest red glows, they witness the universe during its childhood. That effect creates a natural timeline without human clocks, without calendars, without any frame other than distance. A galaxy far away reveals two facts at once. 1. It sits at an enormous remove from the Milky Way. 2. It displays an ancient version of itself. Even the closest major neighbor, Andromeda, shows an older self through the thin delay built into light travel. Andromeda sits roughly 2,537,000 light-years from Earth. That means the light seen through telescopes today departed when early human ancestors walked on Earth without modern civilization, cities, writing, or knowledge of the sky. If the Milky Way contained a civilization watching Earth from Andromeda's location, that civilization would see no modern humans, no oceans filled with ships, no artificial lights circling the planet, and no evidence of modern life. Every glimpse through space carries ancient scenes. When telescopes detect extremely distant galaxies discovered through infrared surveys, the light recorded left those galaxies when the universe contained only primitive structures. Those galaxies existed during an epoch when the first waves of star formation transformed clouds of cold hydrogen into blazing spheres. Over enormous distances, the bright ultraviolet radiation those earlier stars emitted shifted into infrared wavelengths due to cosmic expansion. Telescopes on Earth and in orbit record those stretched wavelengths. Every faint point demonstrates a moment frozen during a period billions of years before Earth formed. The universe has an age near 13,800,000,000 years. When astronomers gather light from sources within the first few 100 million years after the cosmic origin, They see objects nearly as old as time itself. Instruments detect the faint glow from neutral hydrogen during early epochs. Every photon recorded carries a story older than any structure familiar to humans. This effect means cosmic distance behaves like a museum corridor built along a line of light years. The deeper the view, the older the scene. Travel toward a distant galaxy would never grant an up-close view of its present state. Any traveler approaching that galaxy would experience a confusing shift. The light ahead would grow younger during the journey, revealing newer stages of its evolution. The traveler would never witness the galaxy's true present, because that present moves forward through time faster than any spacecraft could chase it. Even at light speed, travel through the universe remains nearly pointless for human lifetimes. Human experience stretches over decades. Generations extend over centuries. The universe stretches over billions of years. Human timescales vanish compared to cosmic timescales. Consider a voyage toward Andromeda at a fraction of light speed. Suppose a craft reached 90% of light speed. The crew would still require millions of years for the journey. Entire human civilizations would rise and fall while the craft covered only a small fraction of the distance. Even at light speed, which no known object with mass can reach, the traveler would still require millions of years. The crew would never survive the trip. Generational ships might attempt it, yet those ships would need thousands upon thousands of generations before arrival. That hopeless comparison inspired a famous teaching tool known as the cosmic calendar. This concept compresses the age of the universe into a single standard Earth year. On that scale, the cosmic origin occurs on January 1st at midnight. The first stars ignite late in January. The first galaxies take shape in March. Heavy elements appear much later, delivered through violent deaths of early stellar generations. The Milky Way's disk settles into form through the middle of this compressed year. The solar system arrives during early September. Life on Earth emerges during that same month, rudimentary and simple. Complex organisms appear during November. Dinosaurs roam during the week leading toward Christmas. Humans arrive during the final minutes of December 31st. Recorded human history fills only the final seconds before midnight. Entire civilizations, technologies, and generations occupy an interval so small that it barely registers on the cosmic calendar. That comparison highlights how insignificant human timescales appear on cosmic scales. Travel toward another galaxy requires billions of years. Human life covers only seconds of that timeline. Even advanced propulsion breakthroughs would not change that problem. Nuclear engines, fusion engines, antimatter engines, and exotic drives might permit motion through interstellar space at high speeds, yet nothing removes the limit imposed through cosmic distance. Light remains the speed limit for all information transfer. No physical object with mass can reach that velocity. Every journey falls short. No traveler can witness their modern appearance unless that traveler waits through the entire time delay. Any voyage toward a distant galaxy would create a strange effect. At launch, the traveler sees a very ancient version. During the journey, the traveler moves into regions filled with progressively younger photons. Near the end of the trip, the traveler might see the galaxy during a far later stage of development, yet never reach the moment of today's version. That moment sits millions or billions of years ahead of the traveler's path. Cosmic expansion magnifies the difficulty. The universe does not remain static. The space between galaxies grows over time. Every galaxy outside the local group drifts outward with increasing speed. This expansion does not involve galaxies rushing outward through a pre-existing void. It involves the stretching of space itself. The distance between clusters grows because space stretches between them. This effect causes galaxies to recede from one another with speeds linked to their distance. Greater distance produces greater recession speed. Cosmic expansion remained unknown during early stages of astronomy. When Edwin Hubble measured the distances to galaxies through the brightness of Cepheid variable stars, he discovered a trend in their motion. Light from most of those galaxies showed a shift toward red wavelengths. A red shift reveals motion away from an observer. The farther a galaxy sits, the greater the redshift. This pattern shows that the universe expands uniformly on large scales. Every region moves away from every other region when viewed on cosmic distances beyond gravitationally bound structures. Cosmic expansion does not pull everything apart. Gravity holds the Milky Way together. Gravity holds the local group of galaxies together. Gravity binds satellite galaxies around larger hosts. Those regions resist expansion. Farther out, expansion dominates. Clusters recede from one another. Superclusters drift outward, leaving enormous voids between them. The cosmic web stretches like a vast fabric dotted with knots where clusters sit and filaments where galaxies form. Everything in that web gradually moves away from everything else. Over long periods, expansion produced a strange side effect that surprised researchers. The expansion rate does not slow. The expansion rate accelerates. Something in the universe pushes galaxies apart with increasing strength. That unknown force gained the name dark energy. It fills space without producing light, heat, or detectable particles. It influences everything simply through its effect on expansion. Acceleration means that galaxies at great distances move away faster than galaxies nearby. In extremely distant regions, recession speed exceeds light speed. That does not violate the speed limit because recession originates from the growth of space itself, not motion through space. When space stretches, two distant points separate without either point moving locally. Light cannot cross enormous distances once those distances expand faster than photons can cover them. Beyond a certain limit, light from distant galaxies never reaches Earth. Those galaxies drift out of the observable region forever, leaving behind only the faint glow produced during their younger ages. The accelerating universe creates an enormous barrier for travel. A craft moving at high speed might attempt a journey toward a distant galaxy, yet the target recedes more rapidly over time. Even if the craft closes some distance early in the journey, the target might eventually drift away faster than the craft can chase it. That effect creates unreachable regions. Those unreachable regions increase over time. Every moment places more of the universe forever out of reach. Look-back time reveals ancient scenes, but cosmic acceleration ensures that future scenes from those regions grow dimmer, colder, and eventually disappear from sight. Even nearby regions inside the observable universe create impossible challenges. The distance to Andromeda seems small compared to the size of the universe, yet that distance still places the galaxy far beyond any human travel plan. The local group contains only a handful of large galaxies, with the Milky Way and Andromeda dominating the structure. These galaxies move toward each other through their mutual gravitational pull. Despite cosmic expansion elsewhere, the local group falls inward. The two large galaxies drift closer and will eventually merge in several billion years. That inward drift does not help travel times for humans. The timescales remain far beyond human lifespan, human civilization, and even human species survival. Cosmic expansion shapes the appearance of look-back time. Photons leaving distant galaxies stretch during their journey through expanding space. Their wavelengths pull toward the red region of the spectrum. That stretching reveals the expansion rate at different epochs. When telescopes measure redshifts from early galaxies, they gather information about how quickly the universe stretched during those ancient times. Through repeated observations, scientists reconstruct a timeline of expansion rates, showing the shift from early slowing when gravity dominated toward later acceleration when dark energy dominated. Redshift also changes how galaxies appear. A distant galaxy loses energy during its photon journey. That energy loss dims the galaxy. Even large galaxies become faint smudges through extreme distances. Only powerful instruments can detect them. Even then, those faint sources disappear beyond certain thresholds. The observable universe has a limit not through size alone, but through the race between light and expansion. Light attempts to reach Earth. Expansion stretches the distances. Beyond a certain point, expansion wins. Look-back time produces the strange fact that the most distant objects display their earliest forms only. No telescope will ever view their mature state. Their mature state might already exist, yet their photons cannot reach Earth. Those distant galaxies drift away faster than light can travel. The view humans receive grows older during the journey backward, not forward. The deeper the view, the earlier the snapshot. Nothing human or machine can reach them. Even if a craft launched at enormous speed, the craft would always chase a target moving away at an even greater pace. The target stays ahead, locked behind a moving horizon that no traveler can cross. The cosmic calendar compresses this entire story into a human-friendly scale. When the universe fits within a single year, the early ignition of stars during January and the formation of galaxies during March create the foundation for everything that follows. Heavy elements appear during middle months. Solar system birth occurs during early September. Earth's life begins shortly afterward. Complex life emerges in late months of the year. Humans appear during the final instant of December 31st. When the cosmic calendar highlights the nearly infinite reach of cosmic ages compared to human ages, it becomes clear that even near light speed travel accomplishes nothing meaningful for human travelers. A journey toward a distant galaxy might require millions of years, even at 90% of light speed. Using the cosmic calendar, that journey would consume months of the compressed year. Human lives occupy nothing more than a thin moment in that year. Generational survival over millions of years requires biological continuity through thousands of generations. No society ever maintained continuity over periods, even a fraction of that length. Archaeological evidence covers a tiny fraction of human existence. Recorded history covers a far smaller fraction. Civilizations rise, fall, collapse, vanish, and get replaced within millennia. Millennia themselves vanish on cosmic scales. They barely make a dent in look-back timelines. Cosmic acceleration increases the gulf. Even if a craft reached extraordinary speeds, the destination would not remain still. The universe expands everywhere beyond gravitationally bound regions. Expansion does not wait. At larger distances, expansion pushes galaxies apart faster. The craft moves forward, yet the target moves away. The target accelerates outward. A distant galaxy recedes more rapidly each moment. The chase becomes endless. Every nearby galaxy outside the local group recedes at a measured rate. The rate grows with distance. Beyond a certain threshold, entire regions of the universe recede faster than any craft can pursue. These unreachable regions expand over time. The observable universe grows older and dimmer through cosmic stretching. Eventually, only the local group remains visible from a distant future vantage point. Everything else fades beyond the horizon of detectability. That future scenario remains billions of years away, yet it demonstrates how expansion isolates regions over time. When instruments capture faint red galaxies at extreme distances, they capture a time when the universe contained far fewer elements. Stars glowed blue-white. Supermassive black holes grew rapidly. Galaxies collided often. Their chaotic forms spread light through irregular shapes. Dense gas clouds collapsed into stars rapidly. That era flickered with intense ultraviolet radiation. The photons from that period now reach Earth, stretched into infrared wavelengths due to expansion. Those photons allow researchers to witness the universe during infant stages. Cosmic acceleration ensures that the timeline revealed through look-back will never reverse. Light recorded today tells a story from ancient epochs. Light recorded tomorrow tells a slightly younger story from the same epochs, because more photons reach Earth from slightly newer moments in those distant galaxies. Yet eventually those galaxies cross a threshold where their newer photons never reach Earth. Their ongoing evolution becomes impossible to study. Only ancient light remains visible. Travel through the universe cannot solve that problem. Look-back time means any journey toward a distant galaxy brings a traveler through a gradient of light-age differences. During that journey, the traveler intercepts photons that departed at later moments. The traveler would witness the galaxy growing younger, not older, during the approach. The traveler would see the galaxy move through stages of formation toward maturity. Yet the traveler would never reach the galaxy's true current state, because the delay remains too large and the expansion too rapid. The mismatch between cosmic timescales and human timescales never disappears. Even if humans lived thousands of years, the mismatch would remain. Even if biological or technological enhancements extended lifespan further, the mismatch would remain. The universe measures change over billions of years. Galaxies evolve through epochs so long that human minds cannot intuit their length without tools like the cosmic calendar. A lifetime occupies an interval too small to register. Cosmic acceleration places additional challenges on observation itself. Distant galaxies drift outward into colder, darker regions of the expanding space. Their redshift increases, their light dims, their spectral features blur. Detection requires larger telescopes with greater sensitivity. Eventually, no instrument can capture photons from regions beyond certain distances, not due to technological limits alone, but due to the horizon created through acceleration. That horizon grows in a future where the universe expands faster with time. No traveler can approach that horizon. The horizon moves outward with increasing speed. The traveler cannot cross it, cannot approach objects beyond it, cannot retrieve information from regions outside it. That barrier remains permanent on cosmic scales. It does not behave like a wall. It behaves like a region where distances grow too fast for photons to bridge. Look-back time, cosmic expansion, and the cosmic calendar together create a picture of a universe where travel between galaxies remains unattainable for humans. Even knowledge of distant galaxies depends on ancient light alone. The expansion ensures those galaxies move farther away with each passing moment. The cosmic calendar compresses the entire story into a single year, revealing the narrow window in which human life exists. That window grows small enough that any dream of travel toward another galaxy becomes unrealistic. Light carries messages from distant regions. Those messages reveal ancient events. The present state of distant galaxies remains hidden. The future states remain hidden. Only the past reaches Earth. Humans live in a universe where direct contact with distant galaxies remains impossible. The cosmic horizon grows. The universe stretches. Human time remains short. Human reach remains tiny. Look-back time shows the past only. The future remains out of reach forever. The physics of space travel. The moment a spacecraft rises above Earth's atmosphere, it enters a universe ruled by rules that do not bend for convenience or human comfort. Every movement demands energy, every change in speed pulls on fuel reserves with ruthless precision, and every dream about traveling between the stars runs into the same concrete wall. Physics sets limits that nothing can cheat. The universe does not care about any species' hopes for reaching distant galaxies, and the very structure of reality shapes what is possible. Light moves at a speed that nothing in the universe has ever outrun, and every attempt to push a spacecraft toward that barrier reveals how much effort the journey demands. Space travel seems simple when viewed from Earth, where rockets lift satellites or cruise into orbit as though all that is required is enough thrust and patience. Once the goal extends past our moon and moves toward stars or galaxies, the numbers expand into scales that twist every familiar sense of distance, speed, and time. Relativity sets the ultimate speed limit. Light crosses vacuum at 299,792 kilometers every second, a number so enormous that it feels abstract. On Earth, nothing in everyday life comes close to this pace. Cars, planes, even the fastest jets struggle to kiss a fraction of that number. Photons move through space with no mass holding them back, allowing them to respond to every shove instantly. Spacecraft contain mass, and mass resists every attempt to accelerate. Relativity reveals that the faster an object moves, the more energy it takes to push it faster. Near light speed, the energy demand grows toward infinity. No engine can deliver infinite energy. No fuel source can bridge that gap. This single truth crushes every fantasy about outrunning light. Imagine a ship trying to reach a distant galaxy. Many galaxies sit millions or billions of light years away. Even if a craft reached 90% of light speed, It would still need millions of years to cross that gulf. Relativity stretches time in interesting ways during high-speed travel, and travelers near such speeds would experience time passing slower than people back home. But the distance between galaxies remains so enormous that even this effect cannot rescue the journey from the scale of the cosmos. From the traveler's point of view, a few decades or centuries could pass inside the ship, but outside, entire civilizations would vanish before the craft even reached the halfway point. The traveler would be stepping into an unknowable future, and the destination would remain far beyond reach because the universe continually expands, dragging galaxies farther apart. Pushing near light speed for the sake of intergalactic travel becomes a pursuit that consumes gigantic amounts of energy with no realistic payoff. Energy defines everything in spaceflight. Rockets must fight gravity during launch, but once in space, the challenge transforms. Without friction or air resistance, movement becomes simpler in one sense, though every act of speeding up or slowing down burns propellant. To accelerate a spacecraft to even a fraction of light speed demands energy that surpasses anything humans have ever harnessed. Lifting a rocket off Earth requires chemical fuel. It explodes in controlled ways, releasing energy that pushes exhaust downward and the rocket upward. Chemical rockets work for reaching orbit or traveling within our solar system. Their energy density cannot support relativistic speeds. Even the best chemical fuels barely scratch the level needed for long-distance travel through the galaxy. Chemical rockets operate through reactions between molecules that store modest amounts of energy. Their velocity limit, called specific impulse, remains too low for high-speed journeys. Any craft relying solely on chemical propulsion cannot climb to speeds required for interstellar travel unless it carries absurd amounts of fuel, so much that the mass of the rocket becomes impossible to launch. The rocket equation punishes every attempt to pack more fuel. The heavier the rocket gets, the more fuel it needs, which adds even more weight, trapping the design in a loop that ends with a ship too massive to move. Engineers have explored many methods to escape this trap, and each method reveals promises and barriers that shape the future of deep space exploration. Nuclear thermal propulsion takes advantage of energy stored inside atomic bonds. Instead of reacting chemicals, this concept heats a propellant with a nuclear reactor. Heating hydrogen to extreme temperatures creates thrust stronger than chemical engines and significantly improves efficiency. A spacecraft equipped with a nuclear thermal system could reach other planets far faster than current rockets. The heat transfer method still cannot push a ship through interstellar space at a meaningful percentage of light speed. The energy density of nuclear fission improves performance, though the numbers remain far from the scale needed to cross tens of thousands of light years. Nuclear thermal engines provide a step forward, not a final solution. Engineers have also explored nuclear fusion propulsion. Fusion reactors mimic the process powering stars. When light atomic nuclei fuse into heavier ones, energy floods out in massive quantities. A spacecraft using controlled fusion would have an energy source much more powerful than fission. Many scientists argue that fusion propulsion could shorten interstellar travel times from millennia to centuries or even decades. Though this vision depends on future breakthroughs in reactor confinement, fuel availability, and heat management. Every design faces the same physics. Accelerating large mass to extraordinary speeds requires extraordinary energy. Even a fusion-powered craft pushing toward 10% of light speed would still need careful design to store and handle the energy it produces without melting the ship. Ion drives represent another direction. These engines use electric fields to accelerate charged particles, often xenon ions, out of the engine to create thrust. Ion drives produce gentle but continuous acceleration. Over long periods, they can reach impressive velocities. They consume fuel far more efficiently than chemical rockets. Spacecraft like NASA's Dawn mission used ion propulsion to travel between asteroids using minimal propellant. Ion engines shine in missions where patience is acceptable. Their thrust remains weak, like a slow breeze nudging a ship across the ocean. Reaching high speeds requires months or years of constant thrust. For interstellar distances, ion propulsion remains too slow. The energy needed to power the onboard systems and maintain thrust for such long journeys also creates obstacles. Antimatter propulsion stands at the extreme end of theoretical designs. When matter meets antimatter, the two annihilate, releasing energy with almost perfect efficiency. A spacecraft fueled with antimatter could generate titanic thrust. 1 gram of antimatter releases as much energy as multiple nuclear bombs. This makes antimatter propulsion appear like the ultimate dream for interstellar travel. The problem sits in the details. Antimatter is incredibly difficult to produce. Particle accelerators can create tiny amounts of it at enormous energy cost. Storing antimatter safely requires electromagnetic traps that prevent contact with ordinary matter. Even a slight containment failure would destroy the spacecraft. Producing enough antimatter to fuel a starship would demand energy outputs greater than entire national grids. The engineering required to store and use antimatter thrust remains far outside current capabilities. Some researchers explore fusion pellet propulsion, where small fusion capsules ignite behind a spacecraft to push it forward. Others examine magnetic sail concepts, where giant superconducting loops interact with solar wind or interstellar plasma to create drag or thrust. Light sails belong to the same family. These large, ultra-thin reflective sheets capture momentum from photons. Photons have no mass but carry momentum, so when they bounce off a reflective surface, they give it a push. A starship pushed with laser beams aimed from Earth or the Moon could accelerate slowly but steadily across interstellar space. Projects like Breakthrough Starshot propose sending small probes toward nearby stars, with ground-based lasers shining on tiny light sails. Such probes could reach 20% of light speed, though they would be no larger than a computer chip. The concept cannot scale up to human-sized ships without energy demands rising beyond anything realistic. Relativistic speeds force increasing mass. When velocity approaches light speed, the ship's effective mass skyrockets. Every bit of fuel must push not only the ship, but the fuel itself. The amount of energy needed to shave off each additional % of light speed becomes monstrous. Even turning or altering course becomes nearly impossible because the ship's momentum grows enormous. A starship near light speed must travel in nearly a straight line through the galaxy, hoping no cosmic hazards drift in its path. The crew inside would feel the distortions cause time running slower for them compared to anyone left behind. A round trip to a nearby star, even at optimistic speeds, would stretch into centuries back on Earth. Crews would return to a future they never expected. Intergalactic travel introduces even harsher limits. The distances between galaxies exceed anything inside the Milky Way. Andromeda sits more than 2 million light-years away. Light takes that long to cross the void separating our galaxies. A ship traveling at 99% of light speed still needs over 2 million years from the perspective of the universe outside. For travelers on board, time would pass slower, possibly giving them the sense of a much shorter trip, though outside civilization would have evolved into something unrecognizable. Any return home transforms into an epic journey into a far future Earth or a world that no longer exists. The energy needed to accelerate a starship containing humans to such speeds surpasses the output of entire stars. A functioning intergalactic vessel would require engines powerful enough to distort the very space around them. Human engineering cannot approach such scales. Even gathering enough material to build the ship would be nearly impossible because the structure must survive collisions with dust and gas at near light speed. A grain of sand hitting the hull at such speeds releases energy equal to an explosive device. Shielding must withstand constant bombardment from microscopic particles turning into plasma on impact. Long journeys at relativistic speeds place the spacecraft inside a furnace of radiation created through interactions with cosmic particles. Every protective layer adds mass, and every increase in mass demands more energy for acceleration. Galactic gravity creates another cage. The Milky Way holds hundreds of billions of stars. Their combined gravity, along with gas clouds and an enormous halo of dark matter, keeps the galaxy bound together in a gravitational structure. To leave the galaxy permanently, an object must reach escape velocity. Near Earth's position, this value sits around 500 to 600 kilometers per second. This speed dwarfs anything human spacecraft can achieve. Voyager 1, the fastest craft to leave the solar system, moves around 17 kilometers per second. The Parker Solar Probe, which dives near the Sun and borrows solar gravity to accelerate, reaches around 200 kilometers per second. Even that record remains far below the speed needed to break free of the galaxy's pull. Hypervelocity stars show what escaping the galaxy actually requires. These rare stars move so fast that they eventually drift into intergalactic space. Their speeds come from extreme events, such as interactions with the supermassive black hole at the center of the Milky Way. When a binary star system wanders too close to the black hole, one star can be captured while the other is flung outward at incredible speed. These stars reach over 1,000 kilometers per second, enough to tear themselves free from the galaxy. Even small planets near such stars can be dragged along for the ride if their orbits survive the violent encounter. Hypervelocity stars reveal that escape from a galaxy demands an extraordinary gravitational slingshot. No engine built on Earth could replicate that kind of acceleration. Every spacecraft humanity has launched remains trapped inside our cosmic home. They drift through interstellar space at peaceful speeds, compared to the runaway objects that tear across the galaxy. Even if a spacecraft relied on advanced propulsion and constant acceleration for decades, reaching galactic escape velocity would require engineering beyond anything imaginable today. The energy cost grows with every kilogram of mass on board. Humans need life support, radiation shielding, water, oxygen, food, and artificial gravity solutions. Each system adds weight. Each bit of weight adds to the energy toll for acceleration. Relativity also affects time in ways that reshape long journeys. When a spacecraft moves closer to light speed, clocks inside run slower compared to clocks on Earth. Time dilation could let future explorers travel far into the galaxy while experiencing only years or decades, though travelers would return to a future Earth changed beyond recognition. This effect cannot accelerate travel in the sense of shortening the actual path between 2 points. Relativity preserves the light speed limit and refuses to grant shortcuts. Time stretches for travelers, not for the universe around them. Energy demands grow even worse when discussing deceleration. A ship racing toward another star must slow down once it arrives. Stopping requires as much energy as speeding up. Any starship reaching near light speed must reserve enormous fuel supplies to reduce velocity without vaporizing crew members through extreme braking. Magnetic sails or interstellar drag devices might help, though these systems remain conceptual and rely on environmental conditions that cannot be controlled. Every journey through space reveals barriers rooted in fundamental laws. The vacuum between the stars feels empty, though it still contains particles, magnetic fields, cosmic radiation, and gravitational gradients. A ship attempting to cross the galaxy at extreme speed collides with this environment constantly. Radiation exposure intensifies as velocity increases because cosmic rays strike the ship with more energy. Shielding must protect the structure and crew, though shielding adds weight that slows the ship down. Every solution introduces new problems that multiply across the craft. Light travel time shapes navigation. If a star sits 1,000 light years away, any image of that star shows it as it looked 1,000 years ago. If a star flared into a supernova now, travelers would not see it until the light reaches them. This delay complicates every decision during long-range travel. Pilots would navigate using outdated information. A system might appear safe from far away, though a radiation burst or stellar collapse might have occurred centuries earlier. Fuel collection concepts such as ramjets have been suggested, where a spacecraft scoops interstellar hydrogen and uses it for fusion. The density of hydrogen in interstellar space remains extremely low. A scoop must be enormous to capture enough fuel, and the drag caused through interaction with the medium could counter any gain thrust. Many designs struggle with this issue. Space also expands. Distant galaxies move away from us faster over time, pushed apart through dark energy. Any craft traveling far into the cosmos enters a universe where distances constantly stretch. A ship heading toward a distant galaxy might never reach it because the space between them grows faster than the ship moves. Even light cannot chase down objects receding faster than its speed because expansion is not motion through space, but growth of space itself. This effect strengthens over cosmic timescales and places additional barriers on ambitious travel plans. Every technology humans have tested so far remains best suited for travel within the solar system. Chemical rockets lift cargo and crew into orbit. Ion drives move satellites and probes between planets. Solar sails drift through space with gentle acceleration. Nuclear concepts wait for regulatory approval and engineering breakthroughs. Fusion engines spark interest, though remain untested outside laboratories. Antimatter propulsion exists mainly on whiteboards and simulations. Every path points toward the same truth. Mass demands energy to accelerate, and the amount required for interstellar or intergalactic speeds sits far beyond anything a human civilization has developed. Even proposed generation ships, which travel slowly and carry multiple generations of crew, face the limits of cosmic scale. A ship creeping through the galaxy for tens of thousands of years would need constant repair and stable social structures. No metal can last that long without maintenance. No closed ecological system has run for that duration. Micrometeoroid impacts accumulate over centuries, drilling holes through hulls. Radiation damages every molecule in a spacecraft, weakening structure and equipment. The lifespan of a spacecraft becomes a barrier even before speed limits enter the equation. Intergalactic travel remains even more extreme. No structure could survive millions of years in motion through harsh cosmic environments. The ship would endure collisions with dust, energetic particles, and unforeseen cosmic hazards. Stars drift, supernovae erupt, and black holes wander. A ship traveling for millions of years would eventually cross paths with some event capable of destroying it. Time dilation alters the experience for travelers, though it does not make the universe smaller. The distance between galaxies remains the same in every reference frame. A traveler racing toward Andromeda might perceive the journey as shorter, though outside observers would measure millions of years passing during the crossing. Communication becomes impossible. Any message sent back home takes as long to arrive as light does. Any emergency remains isolated forever. No mission control can intervene across intergalactic distances. Even the thought of building a ship capable of reaching relativistic speeds introduces problems that go beyond engineering. Structural integrity under constant acceleration becomes a critical obstacle. A craft pushing toward half the speed of light must accelerate slowly to avoid crushing the crew under intense G-forces. Slow acceleration demands patience measured in years. A propulsion system strong enough to maintain thrust for that long requires exponential amounts of energy. Heat dissipation complicates everything. High-energy engines release heat faster than any radiator could vent into space. Spacecraft cannot rely on convection because the vacuum lacks a medium to carry heat away. Radiation becomes the only method for shedding excess thermal energy. Radiators must be huge to handle the load. Large radiators increase mass and surface area exposed to hazards. No universe-scale shortcut has ever been discovered. Wormholes remain theoretical structures predicted through equations. Stable wormholes require exotic matter with negative energy, something never observed in nature. Even if such structures exist, no evidence shows that they appear naturally in usable forms or that spacecraft could pass through them unharmed. Warp drive concepts face similar obstacles. They demand manipulation of spacetime on scales far beyond any known technology. The energy requirements exceed the mass energy of entire planets or stars. Physics continues to highlight the same message. Nothing in the universe accelerates massive objects near light speed without consequences. Space travel succeeds when missions remain modest in scope. Probes explore planets, moons, and asteroids. Telescopes drift into stable orbits around Lagrange points. Landers crawl across Mars or dive through the ice plumes of moons like Enceladus. These missions fit within the energy budgets that chemical rockets, ion engines, and solar panels can provide. Every step beyond the solar system pushes technology toward a cliff where propulsion and energy limits block the path. The Milky Way remains a sprawling home that no spacecraft can escape through engines alone. Gravity extends its influence across 100,000 light-years. Dark matter deepens this gravitational well. Stars traveling near the edges of the galaxy obey the same gravitational tether. Only objects accelerated through violent astrophysical events reach speeds high enough to flee. Humans will never accidentally stumble upon this kind of boost. Even aligning a spacecraft with the center of the galaxy and attempting to slingshot around the supermassive black hole would not replicate the necessary acceleration, because the maneuver requires a binary companion star to perform the exchange. The deepest truth emerges from the combination of relativity, energy limits, and distances. Every voyage through space becomes a fight against scale. The universe is enormous, and the rules woven into its fabric make high-speed travel nearly impossible for massive spacecraft. Even dreams of crossing the galaxy rely on engineering that remains centuries, or possibly millennia, beyond reach. Light moves freely. Mass does not. The boundary between what moves easily and what requires impossible levels of energy remains the defining constraint on cosmic travel. Humanity might someday develop engines that outperform chemical or nuclear systems, and future missions could reach nearby stars through slow but persistent acceleration. The galaxy will still hold its travelers inside its gravitational cage. Every journey will unfold inside a realm where distances overpower ambition and energy demands grow into skyscrapers that tower over every engine concept. The universe stays immense and unforgiving, waiting in silence as spacecraft try to push through limits that have shaped cosmic motion since the first atoms formed. The space between the stars looks like a clean, empty sea, but the moment a ship tries to move through it at extreme speeds, the calm image falls apart. The interstellar medium is not smooth, gentle, or harmless. It is filled with dust grains that act like tiny bullets, gas clouds that can tear at a hull through constant friction, and cosmic rays that carry enough energy to slice through electronics, human tissue, and shielding that would look strong inside the solar system, but begins to crumble in the raw exposure of deep space. A single grain of dust that floats harmlessly near a star becomes a weapon when a ship reaches a fraction of light speed, because the impact releases energy equal to a small explosion. A steady rain of these particles stretches through every arm of the Milky Way, and a ship traveling for thousands or millions of years across that region would face non-stop collisions that slowly eat through armor, wiring, data lines, radiation shields, and anything that tries to hold the vessel together for the long journey. Even the strongest materials created on Earth begin to break down when they are struck again and again at enormous relative velocities, and a single breach in the wrong place could disable a drive, depressurize a living area, or destroy a power system. There is no mechanic floating nearby who can fix it, and no rescue vehicle waiting to dispatch. The ship is alone, surrounded by dust and gas that never stops coming. Cosmic rays are even more unforgiving. They are particles accelerated to insane speeds by violent events scattered across the galaxy, and they carry enough energy to punch through anything a ship can reasonably carry. Inside the solar system, these particles already cause issues for satellites, astronauts, and sensitive detectors. But in interstellar space, they are even more common, more energetic, and harder to block. Radiation from cosmic rays damages DNA, scrambles electronics, interferes with guidance systems, and slowly cooks every system that tries to run for long periods without maintenance. This radiation would continue hitting the ship without any break for millions of years, because the galaxy never stops producing events that sling high-energy particles outward. Even the strongest shielding grows weaker through constant bombardment, and over unimaginable stretches of time, the radiation eats through thick layers of protection. For a short mission, a ship might survive. For a journey across millions of years, the accumulated damage becomes overwhelming. Then the crew faces the bigger monsters that wait inside the larger galaxy. A star that looks calm for billions of years can suddenly detonate in a supernova. That explosion floods space with shockwaves, radiation, and high-energy particles that can sterilize everything within vast distances. Even a ship built to endure smaller cosmic rays could be overwhelmed instantly if it passes near a supernova at the wrong moment. The same danger rises from gamma-ray bursts, which send out narrow beams that can sweep across large sections of the galaxy. A single burst aimed in the direction of the ship would deliver more energy than the structure could possibly handle, leaving nothing but drifting fragments. These events remain unpredictable because the life cycles of massive stars are long and complex, and a ship cannot rely on charts created millions of years earlier because the entire neighborhood of stars would have changed while it was still somewhere in the void. Rogue black holes add another layer of danger. They drift across the galaxy after their parent systems are disrupted or after collisions fling them from stable positions. They emit almost no light, which makes them nearly invisible until a ship approaches too closely. The gravity around them distorts space, alters the path of particles, and creates tidal forces that can tear a vessel apart long before the crew realizes what they are approaching. Even if the black hole is small, the interaction between the ship's speed and the black hole's warped space can lead to violent gravitational stresses. If the ship tries to avoid it at the last second, the enormous velocity makes any maneuver extremely difficult, because even a small change in direction requires immense amounts of energy. When all these dangers are added together, the idea of surviving a voyage that stretches across millions of years begins to fall apart. Technology cannot repair itself forever. Materials cannot withstand endless impacts from dust grains moving at relativistic speeds, and biological life cannot stay alive without constant shielding from radiation that grows stronger the farther a ship travels outside the protective bubble created around the Sun. The galaxy is not a peaceful ocean. It is a giant environment filled with chaotic forces that tear at anything that moves through it for too long. Even if a ship escapes the immediate neighborhood of the solar system and finds a stable path among the stars, the constant hazards slowly stack up until something critical fails. Once that happens, the journey ends, not with drama, but with quiet decay drifting through cold space. On top of every danger inside the Milky Way, there is the deeper truth that the universe is stretching. This expansion was first discovered when distant galaxies were found to be moving away from us, and the farther they are, the faster they appear to recede. This happens because space itself is growing. Galaxies are not shooting through pre-existing space in every direction. Space is expanding everywhere at once, so the distance between galaxy groups increases without any engine pushing them. This expansion is driven by a mysterious form of energy woven into the fabric of the cosmos, something scientists call dark energy. This unknown force steadily accelerates the growth of the universe, and the more space that forms, the faster the expansion becomes. The change is slow on human scales, but enormous when measured across billions of years. The value used to describe the expansion rate is called the Hubble constant, a number that represents how fast galaxies appear to move away for every megaparsec of distance. A megaparsec is over 3 million light-years, and each one multiplies the apparent speed of a galaxy's recession. If a galaxy is hundreds or thousands of megaparsecs away, the expansion pushes it at unbelievable speeds that continue to rise with time. The accelerating universe means the future will see galaxies pulling away even faster than they do today, not because they use engines or gravitational slingshots, but because space itself continues to stretch around them. This expansion creates limits that no ship can cross, no matter how powerful or advanced. There is a boundary called the cosmic event horizon, a distance beyond which galaxies move away so rapidly that no signal, no spacecraft, no beam of light from our region can ever catch up to them. They are not moving through space faster than light in the usual sense. The expansion of space increases the gap between us at a rate that outpaces even light's ability to close it. Anything beyond this horizon remains forever out of reach. The concept is not poetic or philosophical. It is a physical barrier created by the accelerating expansion. Even if a ship could travel at the ultimate limit imposed by the speed of light, it would still fall behind that expansion and never reach those galaxies. This event horizon grows more restrictive as the universe ages. The acceleration caused by dark energy widens the gap between galaxy groups until each group becomes isolated within its own bubble of space. The Milky Way and the Andromeda Galaxy, along with a few smaller galaxies in our local group, will eventually merge into a single system. But everything else will drift farther away, pushed toward a future where the night sky outside this merged structure contains no other galaxies at all. A ship trying to reach those distant galaxies would find the target running away faster every moment, like chasing something that moves faster each second. No amount of determination, no improvement in technology, and no increase in propulsion efficiency can overcome the expansion because the boundary is created not through engineering challenges, but through the nature of space itself. The ship would also face the cold truth that escaping the galaxy does not guarantee escape from danger. Even if it passes the halo of stars, clears the regions full of dust and gas, and avoids supernovae and rogue black holes, the voyage would still stretch into a future where galaxies continue to recede faster and faster. The ship would drift through extremely thin intergalactic gas, a region almost empty compared to the Milky Way, yet still sprinkled with particles that become dangerous at extreme speeds. The radiation from cosmic rays would be even harsher without the magnetic fields produced within galaxies. The hull would continue absorbing damage slowly and silently. Every system would age, wear down, and fail long before the ship could cross distances measured in many millions of light years. The accelerating expansion also means the ship would never reach regions moving beyond the event horizon. Even if it points toward a galaxy that is still within reach today, the expansion might push that galaxy beyond the horizon during the journey. Once that happens, there is no turning point where the ship can correct its course or accelerate enough to regain lost ground. The destination simply slips away forever. A target that exists at the start of the journey may disappear from the realm of the reachable before the ship even finishes a small portion of the trip. Inside the Milky Way, the hazards are already overwhelming, but outside it, the scale becomes even more unforgiving. The void between galaxies stretches across distances that take millions of years even for light to cross. A ship moving at any realistic fraction of light speed takes a span of time that dwarfs human lifetimes, technological eras, languages, cultures, and entire civilizations. A journey through such distances demands stability that no machine or organism has ever demonstrated. The ship must remain intact while carrying its own environment. The environment must remain stable while radiation attempts to destabilize every molecule. And the passengers, if they exist, must have a way to survive uncountable generations without the ability to interact with anything beyond their ship. This long voyage through an expanding universe turns into a story where the destination grows farther away every moment. The space behind the ship stretches too, meaning there is no sense of traveling through a fixed landscape. Everything changes. Distances increase while the ship tries to move across them, and the expansion ensures that no matter how powerful the engines are, the limit imposed by the speed of light always wins. Even a craft capable of reaching speeds that break modern imagination would still remain trapped in a cosmic environment where expansion continues to accelerate. The dream of crossing to other galaxies becomes more like a dream of outrunning the universe itself. The forces shaping the cosmos are not obstacles that can be engineered around or pushed aside. They define the rules of the environment. Radiation flows through every region, dust grains continue to drift, supernovae erupt without warning, black holes roam silently, and the expansion grows stronger over time. A ship might escape the immediate grasp of the Milky Way's gravity, but it would never outrun the deeper structure of the universe. The universe is vast, wild, and filled with regions that no traveler can ever reach, not because of lack of creativity or ambition, but because the fundamental nature of space sets limits that no propulsion system can overcome. Even the most advanced civilization imaginable would face these same boundaries. The interstellar medium would still strike their ship, the radiation would still tear at materials, supernovae would still blast through nearby regions, rogue black holes would still drift unnoticed, and the accelerating expansion would still push distant galaxies out of reach. Nothing in the universe stays still. Everything moves, evolves, and shifts across cosmic time. A ship trying to cross the gaps between galaxies becomes a small object trying to survive hazards that cover millions of light years, while the universe keeps expanding around it. Even if a ship could launch with perfect technology and flawless engineering, the endless stretch of time needed for such a journey would allow every danger to accumulate until survival becomes impossible. The cosmic event horizon ensures that some places remain forever beyond reach. The accelerating universe guarantees that more and more galaxies cross that horizon over time. The interstellar medium presents hazards that never fade. The Milky Way's own dangers follow the ship until it leaves the halo, and the long intergalactic journey offers no safe haven, no shortcut, and no steady ground. This is why crossing to other galaxies is not simply a matter of speed or engineering. It is a battle against the nature of space itself, a battle that no vehicle, no organism, and no machine can win. Black holes and galactic centers. Every galaxy carries its own kind of heartbeat, and the Milky Way's pulse comes from a compact yet unbelievably heavy object sitting at the very center. This object is Sagittarius A*, a supermassive black hole that weighs millions of times more than the Sun. Even though it is far away from every star that fills the sky, its pull stretches across the entire galaxy. Stars, gas clouds, dust streams, and dark matter all follow paths shaped in some way through its grip. Nothing in the Milky Way moves freely without the faint touch of this central mass guiding the overall rhythm of galactic motion. The core acts like an anchor that holds the entire spiral together, even when the outer arms extend across regions far beyond anything the human eye can capture. Sagittarius A** sits in a crowded neighborhood packed with stars that race around it at speeds that look unreal compared to the gentle drift of stars far from the center. Near this core, the gravitational pressure becomes so intense that stars rush through their orbits in tight curves that look almost reckless. They swing through space with tremendous speed, bending their paths sharply as the black hole's hold refuses to loosen. The closer a star comes to the center, the more dramatic the motion becomes. Telescopes have recorded stars looping around Sagittarius A** in patterns that look like glowing threads pulled into sharp bends, proving that something massive and compact controls that region, even though it barely emits light. The orbits form a busy and crowded ballet, where every object responds to a kind of gravity that grows far stronger than anything experienced near the Sun. This influence spreads outward across the entire galaxy. Sagittarius. A** does not pull stars toward itself from great distances, but its mass helps form the deeper structure that every star follows. If the solar neighborhood were shown on a map of the galaxy, the Sun would sit deep inside a region influenced through layers of gravity that link the disk, the bulge, and the halo to the heart of the system. Even stars located tens of thousands of light years away still move within a space shaped through this central weight combined with the rest of the galactic mass. The effect is subtle on the edge of the Milky Way, but the entire shape of the spiral, the winding arms, and the slow rotation all rely on the central mass helping hold the entire disk together as it spins. The idea of a galactic gravitational well helps show how this works. A well is simply a deep region of gravity where anything with mass must follow the slope of the surrounding space. In the solar system, the Sun creates its own gravitational well that keeps planets in orbit. In the galaxy, the combined pull of Sagittarius A*, billions of stars, gas clouds, and a vast envelope of dark matter forms a much larger well that traps everything inside the spiral. The deeper the well becomes, the harder it becomes for anything inside to climb outward. A star far from the center is still inside the well shaped through the whole Milky Way. It moves around the galaxy because the curve created through this mass bends its path. Even if the Sun traveled at incredible speed through the disk, it would still roll along the slopes of this well instead of escaping into the quiet emptiness between galaxy groups. Close to the center, the gravitational well becomes incredibly steep. Sagittarius A* adds a sharp drop at the very heart of that slope. Stars race through that region because they are falling along the steep sides of this central well. Gas clouds stretch into shapes that twist around the core because the slope changes direction rapidly near the black hole. If a gas cloud drifts too close, the intense gradient tears it into thin streams that spiral inward. If a star approaches at the wrong angle, the same gradient grabs it and pulls it into a violent arc, where the star accelerates so fast that the structure of its own surface begins to warp under the force. Some stars escape those close passes through luck or momentum, but others become trapped in even tighter orbits. The Milky Way's core acts like a giant drain that is always spinning, always pulling matter toward its center, always shaping the movement of everything inside its sphere of reach. The place does not look like a calm center of balance. It looks like chaos. Clouds collide and break apart. Streams of gas form rings that light up in infrared wavelengths. Magnetic fields twist into lines that stretch across the region. Stars crash through these chaotic layers, while the black hole keeps everything locked inside its grip. One of the most striking effects of this grip is the way stars and gas become trapped in loops around the black hole. Once an object drops below a certain distance from Sagittarius A*, it becomes locked inside orbits that grow tighter through each pass. Some objects fall into spiraling paths, where each loop brings them closer to the center. Others land in longer, more stable orbits that may last for millions of years. Gas clouds often stretch into spirals that gradually move inward, turning the central area into a disk of inflowing material. The process looks like a never-ending flow, where everything caught in the center continues circling while losing energy over time. Even the fastest motion in this region still follows the giant gravitational pit that Sagittarius A* creates. This trapping effect makes escape extremely difficult. A star inside the central region cannot simply drift outward. The black hole's gravitational hold, combined with the mass of the dense bulge, forms a region where escape demands speeds far beyond what any stable star can generate on its own. Even if a star forms within the inner region with a powerful kick from a stellar interaction, the surrounding mass restricts its motion through a layered envelope of gravity. No star moves through empty space there. Every course must push against a wall of gravitational pull created through billions of solar masses clustered around the core. Humans cannot imagine building a ship capable of fighting through that sort of gravitational structure because the environment near the center is nothing like the calm space near the Sun. Every direction contains obstacles. Clouds collide. Stars sweep through at wild speeds. Magnetic filaments lie stretched across the region, and the gravitational slope steepens rapidly toward the black hole. Even a spectator observing from a safe distance would struggle to process how intense the region feels. Everything races. Everything shifts drastically. Everything responds to forces that dwarf anything near the solar system. In rare circumstances, something dramatic happens in this chaos. A three-body interaction between stars can send one star flying outward with incredible speed. This event creates what astronomers call a hypervelocity star. These stars emerge when a tight pair of stars wanders close to Sagittarius A*. The black hole's gravity grabs one star and locks it into a tight orbit, while the other star gets flung away with enough force to break free from the entire galaxy. The energy exchange acts like a natural slingshot, where the black hole trades one star for the chance to launch another star outward. The launch star leaves the Milky Way entirely and races into intergalactic space at thousands of kilometers per second. Only a handful of these stars have been found because the event is incredibly rare. The process demands precise positions, exact timing, and a highly energetic interaction. The speed of a hypervelocity star becomes possible only through the enormous gravitational field near Sagittarius A*. The star receives energy through the violent exchange, something that no ship could ever copy, because the process depends on mass acting on mass. Hypervelocity stars reach speeds that outmatch anything humans can conceive for spacecraft, not through engines, but through pure gravitational mechanics. The star must fall extremely close to the black hole, come from a tightly bound system, and collide with the gravitational field at the perfect angle. Without those exact conditions, the star either becomes trapped or torn apart. Human technology cannot replicate anything close to this process. A ship cannot survive the environment near Sagittarius A*. Nothing built through human hands could endure the tidal forces near the event horizon, or the powerful radiation generated inside the inner accretion zone, or the intense magnetic fields scattered around the core. Even if the ship approached from a safe distance, it could never use the black hole as a slingshot because the forces involved require stellar masses. A spacecraft is too small to gain anything through such a gravitational exchange. The ship would simply get pulled inward without receiving the energy needed to escape. Hypervelocity stars only form because both objects involved possess enough mass for energy to trade between them through complex gravitational interactions. The paths that lead a star into this rare launch scenario take millions of years to shape. The stars must drift through crowded clusters near the center, interact with other stars repeatedly, and slowly slide toward an orbit that brings them close enough to the black hole. The moment of the slingshot may appear sudden, but the setup spans lifetimes far beyond any species. The star moves through chaos for an enormous stretch of time before the black hole redirects its future permanently. Humans cannot control that process. The scale of mass, distance, and time sits on a level completely separate from anything a civilization can manipulate. Sagittarius A** stands at the center of a gravitational structure shaped across billions of years. The region around it hosts some of the densest areas of star formation in the galaxy. Young stars ignite there. Old stars collapse. Gas clouds fall in and become fuel for new generations. The bulge thrives on this constant cycle of creation and destruction, and every step in that cycle takes place under the eye of the central black hole. The gravitational pressure inside the bulge forms clusters of stars that squeeze together in ways impossible in calmer regions of the galaxy. These clusters drift through the core and eventually move outward or inward depending on slow, long-term changes in their motion. Each star in those clusters carries its own orbit. Some move through long looping paths that reach far from the center before sweeping back inward. Others complete tight circles that never lead them into open space. The entire central region becomes a maze of motion, where every star follows a path determined through gravitational curves shaped through millions of neighbors. All these loops together create a dense system of movement, where the black hole sits at the deepest point of the gravitational map. Everything in that region is always falling inward, and even though many objects circle without falling completely, the slope keeps them locked inside a gravitational bowl that stretches across the bulge. Escape demands speed that almost no natural object ever gains. Hypervelocity stars remain the exception only because the black hole interacts with a pair of stars under the most extreme conditions. Even then, most stars that enter the dangerous zone near Sagittarius A** meet very different ends. Many collapse into tighter paths. Some lose huge amounts of energy as they pass through gas clouds or magnetic structures. Others get ripped into streams of material when tidal forces overwhelm their structural integrity. The region does not offer many exit paths. It offers a long list of ways to become trapped, stalled, redirected, or shredded. The gravitational well of the entire galaxy begins with the dense core wrapped around Sagittarius A*. This inner region sits embedded inside a larger bulge filled with additional mass that contributes to the overall shape of the well. Surrounding this bulge lies the disk where the Sun resides. Surrounding the disk lies the enormous dark matter halo that makes the entire well even deeper and harder to escape. Every object inside rolls along the interior of this structure. A ship leaving the solar system travels outward across the slopes of this well. The farther it moves, the more it must fight the combined mass of the galaxy, not just the mass of the black hole. The shape of the well keeps the galaxy together, and every object inside the galaxy follows this shape, whether it realizes it or not. Sagittarius A* influences even the dark matter near the core because the black hole's mass helps shape the gravitational environment that dark matter responds to, even if dark matter never interacts through light or regular matter. The black hole becomes one of the key anchors that hold the inner region of the halo steady. Every pull, every curve, every rotation pattern stems from this combined structure. The galaxy does not rotate randomly. The spiral arms do not drift on their own. Everything follows curves determined through this central structure. Hypervelocity stars show what happens when a star receives far more speed than it normally should. These rare stars stretch long trails through the galaxy, eventually reaching regions where the gravitational well grows shallow. If a star has enough momentum, it reaches the point where the pull of the galaxy weakens, to the point where the star no longer circles around anything. It breaks free and drifts into space, not bound to any galaxy. Over billions of years, the star moves farther and farther into the emptiness between groups. These stars remain rare because there are only a few ways for an object to receive enough speed to escape the combined gravity of the massive galactic halo. Nothing humans can build could borrow the same mechanism. Hypervelocity stars involve masses greater than entire worlds. They involve gravitational interactions that gather energy from orbits spanning years. They require distances near a black hole that would vaporize any ship that attempts to come near. A ship would be pulled apart through tidal forces long before it could gain speed. Even if it could somehow remain whole, the ship would not have the mass needed to gain the energy transfer that produces the slingshot effect. The black hole would simply swallow the ship or pull it into an orbit from which no escape is possible. The galactic center creates a world of motion that thrives on gravity alone. Sagittarius A* does not need to act actively. Its presence shapes everything around it. The well it sits in forms the bottom of the galactic gravitational structure. Everything above it sits in layers shaped through mass. Stars inside those layers travel through routes sculpted through the slow churning of the bulge and the disk. Even the Sun follows a long path around the center that takes hundreds of millions of years to complete one full orbit. During each orbit, the Sun drifts slightly upward or downward inside the disk, following the small slopes created through the structure of the gravitational well. Every object in the galaxy participates in this long dance, whether it lies near the center or on the edge of the halo. The heart of the Milky Way remains a place humans will never visit. The environment near Sagittarius A* reaches a level of danger that no ship can cross. The gravitational drop becomes too steep. The radiation becomes too strong. The density of stars becomes too high. The sheer activity of the region creates a non-stop storm of physical extremes. And yet this violent core forms the very structure that holds the galaxy together. Without the central mass, the spiral shape would not remain stable. The core acts as the gravitational spine that organizes the entire system, giving the Milky Way its shape and its long-term movement. Hypervelocity stars serve as reminders of how powerful that center can be. They streak outward as runaway travelers that witnessed the full strength of Sagittarius A*. Their paths stretch across the disk and the halo until nothing remains in front of them except intergalactic space. They are the only natural objects that can escape the Milky Way completely, and even they emerge only through the exact alignment of extreme conditions. The presence of these rare stars shows that escape is possible in theory, yet unreachable through any action taken through a species that builds ships through delicate materials and fragile structures. No machine can survive the environment needed to create such a launch, and no civilization can micromanage the gravitational fields needed to reproduce this event artificially. Sagittarius A* will continue shaping the Milky Way far into the future. Stars will continue to fall into its region. Clouds will continue to swirl inward. The bulge will continue to respond to the pull of the core. And the rare hypervelocity star will continue to appear occasionally as the black hole interacts with the tight star systems that wander near the center. The galaxy remains alive with motion and structure because of this central object. Even though the Sun lies far from the core, the gravitational influence of Sagittarius A* continues to help guide the orbit that the solar system follows on its slow journey through the disk. Everything inside the Milky Way remains part of a grand structure anchored through the mass of the black hole. Stellar lifetimes versus travel times to other galaxies. Every star carries a clock built into its core. The moment a star forms from a collapsing cloud of gas and dust, the nuclear reactions inside its center begin the countdown toward its final stage. The Sun sits comfortably in the middle of its own long lifespan, burning hydrogen at a stable pace that keeps the solar system warm and bright. The Sun's life is expected to last roughly 10 billion years from birth to its final cooling stages. This number sounds almost endless from a human point of view, yet in cosmic terms, it is only one chapter in the history of the Milky Way. Stars live, shine, and fade, while galaxies grow, collide, reshape themselves, and drift across the universe. The clocks controlling stars and the clocks controlling galactic motion follow rhythms that rarely match each other. The Sun has lived for about 4.6 billion years. Its remaining time adds up to around 5 billion more before it enters the red giant stage. That future stage will mark a drastic transformation. The Sun will swell until its outer layers reach across the inner solar system. The shape of the orbiting planets will shift. The inner worlds will burn. The energy output of the Sun will grow higher as hydrogen in the core becomes scarce. Eventually, the Sun's outer layers will peel away into space, while the core collapses into a dense white dwarf that slowly cools for trillions of years. The Sun will glow quietly with the leftover heat of its long life. This gentle fading is normal for a star of its size. Yet when you compare that lifespan with the travel time to nearby galaxies, the contrast becomes astonishing. Other galaxies lie so far away that even the most imaginative future ship would not reach them during the Sun's full life cycle. The nearest major galaxy, Andromeda, sits more than 2 million light-years away. A traveler moving at a fraction of light speed would still take longer than the remaining lifespan of the Sun to cross that distance. Even a ship reaching speeds close to light itself would struggle to complete the journey before the Sun transforms into a red giant. The travel times stretch into spans that make the longest human histories look like brief sparks. The numbers become almost unreal when placed side by side. The Sun shines for 10 billion years. The distance to Andromeda equals 2.537 million light-years. If a ship moved at 1% of light speed, it would need more than 250 million years to reach that galaxy. During that time, entire species on Earth would rise and fall countless times. Continents would shift positions. The climate would experience cycles beyond anything recorded in human memory. The Sun would progress through stages of its evolution. The traveler would witness a universe where the home star has changed shape, temperature, and size. Even moving 10 times faster would barely dent the enormous stretch of time. A slightly faster ship traveling at 10% of light speed would still take more than 25 million years to reach Andromeda. 25 million years ago, giant mammals roamed Earth, and ocean life followed patterns that look alien compared to today. The world changed through massive geological processes during those ages. A ship launched during that era would only now be approaching the halfway point. The Sun, once young and stable, would have shifted further toward the later half of its lifespan. Water and heat patterns across Earth would have continued evolving. The world would feel nothing like the one left behind. The traveler would return to a solar system shaped under completely different conditions. Even at half the speed of light, the travel time to Andromeda would reach more than 5 million years. Civilizations built through humans would vanish. Cities would erode. Cultures would fade. Even mountains would reshape through erosion and plate motion during that long stretch. The passengers inside the ship would find themselves tied to a homeland that exists only in ancient records and distant memories. Their descendants would learn that the sun they left behind no longer looks the same. Over millions of years, even the brightness and color of a star shift noticeably. The travelers would live through an environment so different from the original that the connection between origin and destination would lose all meaning. As travel times grow longer, the scale of stellar lifetimes becomes the next point of comparison. Stars heavier than the Sun live far shorter lives. A star 10 times more massive might burn through its fuel within only a few million years, a blink compared to the travel durations needed to cross intergalactic space. If a civilization formed around such a star and attempted to escape to another galaxy, the home star would collapse into a violent supernova long before the travelers reached even a tiny fraction of the journey. Stars lighter than the Sun live much longer, some stretching their lives for trillions of years. Yet those stars provide dimmer light and different conditions for life. The mismatch between stellar clocks and intergalactic distances creates a strange cosmic tension. Stars and galaxies live on scales that ignore each other completely. The Milky Way itself continues to drift toward Andromeda at a speed of more than 100 kilometers per second. Gravity slowly pulls the two galaxies toward a future collision. This slow-motion travel brings the galaxies together in a long, graceful fall across deep space. The timeline for this eventual merger spans more than 4 billion years. This timing nearly matches the remaining lifespan of the Sun before its red giant stage. The idea that the solar system may enter a cosmic collision during the final chapters of the Sun's main sequence life produces a strange sense of overlap between stellar evolution and galactic motion. As the Milky Way and Andromeda draw closer, both galaxies will begin to deform through the gravitational tug between them. Their shapes will stretch. Tidal forces will pull long streams of stars outward. Gas clouds will rush into new paths and spark fresh waves of star formation. The spiral arms that define both galaxies will distort into long arcs that reach across intergalactic space. Some stars will be thrown into distant orbits through the violent exchange. Others will fall inward toward the combined center of mass. During these stages, the Sun will still be burning its hydrogen, slowly inching toward the end of its quiet life. If any civilization still exists during this future time, it will witness a night sky filled with a bright, massive growing shape where Andromeda once appeared as a faint smudge. The two galaxies will begin to blend together into a single huge system known as Milkomeda, a kind of supergalaxy formed through the slow fusion of two spirals. During these phases, the central black holes of both galaxies will drift toward each other and eventually merge, releasing tremendous energy in the form of gravitational waves. Stars that once followed steady orbits will find their paths altered through the new shape of the combined gravitational field. Through all of this, the Sun continues its slow march toward the red giant stage. The clock built into its core ticks downward, while the galaxy around it transforms into something entirely new. The collision between Milky Way and Andromeda will complete long after the Sun's active life ends. The solar system will drift as part of a reshaped galaxy that carries the combined stellar populations of both giants. If any remnants of Earth still exist at that time, they will orbit a white dwarf that glows with the quiet leftover heat from the Sun's collapsed core. The history of humans would be long forgotten, while the merged galaxy continues to evolve and drift across the universe. When you compare all these overlapping time spans, something becomes clear. The galaxy itself evolves on scales that match or exceed the lifetimes of stars. Meanwhile, the journeys needed to travel between galaxies stretch far beyond even those lengths. A civilization hoping to escape the Milky Way would need to survive through epochs that see the home star change shape, the solar system transform, and the galaxy itself become part of a larger structure shaped through collisions with neighboring galaxies. The travelers would live through a universe where everything familiar alters its form long before any destination is reached. The cosmic distance between galaxies stretches beyond the limits of any star's life cycle. Even the longest-lived stars fade eventually. Their complete lifespans reach trillions of years. Yet the space between galaxy groups expands over time through the accelerating motion of the universe. Dark energy pushes galaxies apart faster than they can gravitationally interact, unless they already lie close together. The Milky Way and Andromeda remain bound because they lie near enough for gravity to overcome the expansion of space in their region. Other galaxies drift away at speeds that continue increasing. The vast majority of galaxies already lie far beyond any region that gravitationally connects with the Milky Way, and over time they will cross horizons that separate them forever. These horizons become important when imagining intergalactic travel. If a ship launched toward a galaxy already receding at extreme speed, the ship would find the destination drifting away faster than any approach speed. Even moving close to the speed of light would not allow the travelers to reach galaxy clusters, speeding away faster than the ship can gain ground. The target galaxy would become unreachable, despite constant travel. This effect becomes stronger over time as the accelerating expansion continues. While the Sun completes its life and the Milky Way merges with Andromeda, other galaxies move beyond reach. The travelers would find themselves pointed toward a destination that slips away further each second. This creates a strange comparison. The Sun's life offers a long stretch of time measured in billions of years. Traveling to other galaxies demands even longer stretches, measured in tens of millions, hundreds of millions, or billions of years, depending on the speed of travel. Meanwhile, the universe changes shape as galaxies collide, fade, and drift apart. Any path into intergalactic space crosses a region that transforms even while the traveler moves. The destination may no longer exist in its original form upon arrival. It may merge with another galaxy or collapse around a growing black hole. The path leading toward it may stretch through regions reshaped through cosmic evolution. When comparing stellar lifetimes to these travel durations, the mismatch becomes larger the longer the view extends. A star like the Sun provides a stable environment for billions of years. That seems long enough to support the idea of a slow migration across the cosmos, yet the time needed to reach another galaxy stretches far beyond even that. A civilization born under the Sun would need to survive through ages during which the world changes shape, the star changes brightness, the orbit changes energy, and the entire galaxy reshapes itself through merger. Even the merged supergalaxy may drift into regions of space where neighboring galaxies become impossible to approach because the expansion of the universe pushes them away at extreme speeds. The idea of a stable destination becomes slippery across these immense spans. Suppose a ship aimed for a galaxy located 40 million light-years away. Even at high fractions of light speed, the travelers would face millions of years of travel. During that time, the target galaxy may merge with a second or third neighbor. It may produce a burst of new stars as gas clouds collide. It may change shape entirely. The path leading to the galaxy may pass through regions that become filled with leftover radiation from ancient mergers. Long before the travelers reach the midpoint, the home galaxy may have blended with Andromeda. The Sun may have burned through nearly all its hydrogen. The solar system may carry new shapes through changing gravitational curves. The white dwarf phase may have already begun. These long comparisons create a growing chain of mismatched clocks. One clock controls the Sun, Another controls the motion of galaxies. Another controls the expansion of the universe. The clocks do not match each other, and none of them match the durations needed for intergalactic travel at speeds below light speed. Even if a ship traveled close to the speed of light, the passengers would experience time differently from observers back home due to relativity. Their subjective years may feel short. Meanwhile, billions of years would pass in the outside universe. The stars that lit the sky at launch would fade. The galaxies that filled the cosmic web would shift positions. The future shape of the universe might carry no resemblance to the one known at departure. During all this, the Sun continues following its internal schedule. The pressure and heat inside the core maintain fusion reactions that convert hydrogen into helium. These reactions slowly build a core of helium ash that grows hotter and denser. Over billions of years, the core changes structure. The outer layers respond through shifts in temperature and brightness. The star evolves on a timeline set through nuclear physics. Nothing in the universe can slow or rewind this process. The travel times across intergalactic space ignore that timeline entirely. The travelers, if any exist, become tied to a moving target that shifts under cosmic forces outside their control. The distant future holds even stranger changes. After the Milky Way and Andromeda merge, the new supergalaxy will continue interacting with smaller galaxies in the local group. Some dwarf galaxies will fall inward, others will drift away. The combined structure will flatten into a massive elliptical system where new star formation becomes less common as the gas supply gets used up. The entire region will settle into a calmer, older galaxy. During these phases, the Sun will have completed its transition into a white dwarf. Earth will no longer host life, and the remains of the solar system will drift quietly through a galaxy that shares almost no resemblance to the one that once held humanity. Even during these later epochs, intergalactic travel would still take longer than the entire age of the merged galaxy. The travelers would find that the target galaxy either no longer exists, has drifted too far, or has changed shape beyond recognition. If the travelers aimed for a galaxy already receding at high speed, the destination would move faster than their ship could approach. The travelers would watch the light from the target galaxy shift into longer wavelengths until the galaxy faded from view. They would find themselves traveling through regions of space that expand faster than any possible pursuit speed. No amount of technology could overcome the large-scale motion of space itself. Comparing stellar lifetimes and intergalactic travel shows a picture filled with clocks that do not sync. Stars burn out, galaxies collide, the universe expands. The travelers move through time with bodies shaped through evolution on a small, warm world orbiting a middle-aged star. Everything they leave behind continues evolving long after launch. Every destination evolves during the long journey. Every region between galaxies carries radiation, drifting matter, and expanding space. Nothing stays still for the long stretches of time needed for the trip. The Sun's lifespan seems endless from the view of living creatures, yet it forms only one brief chapter in the story of the Milky Way, and the Milky Way forms only one chapter in the larger flow of the universe. Set the Sun's 10 billion year life next to the tens of millions of years needed for travel at 1/10 light speed, and the gaps become visible. Set the Sun's life next to the billions of years needed for slow travel between galaxy groups, and the gaps widen. Set the Sun's life next to the trillion-year lives of low-mass stars, and the Sun looks short-lived. Set the Sun's life next to the expansion of the universe that pushes galaxies apart forever, and stellar clocks appear tiny. No matter which comparison you choose, travel across intergalactic space stretches into spans that make even stars look temporary. And the Milky Way itself changes on those same scales, shifting shape, blending with neighbors, and drifting across the cosmic landscape, even while the internal life of its billions of stars unfolds. Wormholes, warp drives, and the limits of faster-than-light travel. Human imagination has always sought shortcuts through space. The distances between stars, galaxies, and clusters are immense, stretching across millions of light years, and the natural limits of velocity imposed by the speed of light make real interstellar travel seem nearly impossible. Even at near light speeds, travel between nearby stars takes decades or centuries, and trips to other galaxies extend into millions of years. This extreme reality has pushed both scientists and dreamers to imagine ways to bend, fold, or warp space itself, creating routes that could shrink these distances into manageable spans. Among the most famous ideas are wormholes and warp drives, theoretical constructs that appear in serious research yet remain well beyond practical reach. Wormholes, sometimes called Einstein-Rosen bridges, are tunnels connecting two distant points in space and time. The concept arises from solutions to the equations of general relativity, which show that space-time can curve and connect in unusual ways. A wormhole would allow matter to enter at one location and emerge somewhere far away almost instantaneously, in theory, if a stable wormhole existed between the solar system and a star in another galaxy. A journey that would otherwise take millions of years could occur in moments. The appeal is obvious. Travel through wormholes could bypass the extreme distances that define the cosmos, offering a shortcut across the universe. Yet, the theoretical challenges of wormholes are immense. First, the bridge must remain open. Solutions in general relativity show that any natural wormhole would collapse almost instantly, far faster than anything could travel through it. To prevent this collapse, a hypothetical form of exotic matter is needed, material with negative energy density that would hold the tunnel open. Negative energy has been observed in certain quantum phenomena on tiny scales, but no known form of matter exists in quantities sufficient to sustain a wormhole wide enough to allow a starship or even a human body to pass through. Even the smallest theoretical wormholes that remain open require energies beyond anything humanity could hope to produce for millennia. The mass-energy equivalence principle underlines the scale of the problem. According to Einstein's famous equation, energy and mass are interchangeable. A wormhole capable of bridging a distance of thousands of light-years would require an amount of energy equivalent to converting a mass many times greater than the Sun directly into energy. Creating, containing, and stabilizing such energy is inconceivable with any foreseeable technology. The universe itself contains mass far greater than the Sun in small volumes. Yet harnessing and shaping that mass energy for a wormhole is far beyond any practical scheme. Even the most optimistic projections for energy production, from fusion to antimatter, remain microscopic compared to what is required. Warp drives offer another approach, most famously the Alcubierre metric proposed in 1994. Instead of moving a spacecraft through space at speeds exceeding light, the concept compresses space ahead of the craft and expands space behind it, effectively moving the ship inside a bubble of normal space-time while the surrounding space itself shifts. In theory, the ship could reach distant stars faster than light would traverse the distance, while local relativistic constraints remain unbroken. The Alcubierre drive has fascinated physicists and science fiction writers alike, because it presents a mathematically valid way to cheat the cosmic speed limit without violating relativity in the traditional sense. However, the Alcubierre drive faces challenges that dwarf even those of wormholes. The energy requirements are astronomical. Initial calculations suggested that the drive would need more energy than the mass of all stars in the observable universe. Later refinements lowered the requirements by orders of magnitude, yet the numbers still exceed practical energy sources by factors impossible to overcome. The drive requires regions of negative energy to shape the space-time bubble, echoing the same exotic matter problem found in wormholes. The ship cannot simply push through space faster than light without enormous mass-energy manipulation. While the equations allow the metric to exist on paper, implementing it in physical reality is far beyond the reach of current or near-future technology. Even if a warp drive could exist, other physical limits persist. Gravity on galactic scales exerts forces that shape the Milky Way's structure. Accelerating a warp bubble to near light speeds or beyond does not erase the cumulative effect of the galaxy's mass. Stars, dark matter, and the central black hole create a gravitational landscape that any theoretical warp bubble must navigate. A naive shortcut through space could still lead to encounters with regions of high tidal forces or dense star clusters. The Alcubierre metric assumes smooth spacetime, but the Milky Way contains millions of moving masses that create uneven curvature. The bubble would have to adjust dynamically to avoid catastrophic encounters or collapse under gravitational stresses. Even in a theoretical scenario, interstellar travel cannot ignore the complexity of the galactic gravitational environment. Relativity continues to enforce fundamental limitations even with these speculative methods. Time dilation, energy conversion limits, and the influence of massive objects constrain what a theoretical faster-than-light vehicle can achieve. Wormholes may allow instantaneous travel in theory, yet any matter attempting passage risks extreme tidal forces or collapse. Warp drives may reduce travel time, yet they cannot overcome the need for massive energy inputs or account for all the interactions with the mass of the galaxy. The physics sets clear barriers, even for solutions that remain on paper. Reality imposes limits that mathematical creativity cannot erase. The scale of the problem also emphasizes why these ideas remain speculative. A human civilization would need to generate, control, and manipulate energy far beyond the sun's output to even approach practical use of a wormhole or warp drive. Negative energy must exist in large, controllable quantities, which currently appears impossible. Spacecraft would need shielding against cosmic rays, interstellar dust, and extreme temperatures during travel, all while maintaining a stable bubble or tunnel through spacetime. The challenges combine quantum mechanics, general relativity, astrophysics, and engineering problems that do not scale from laboratory experiments. No laboratory has ever produced the kinds of effects needed to sustain the bubble or tunnel, and scaling from tiny quantum effects to galactic-scale travel introduces uncertainties that are impossible to resolve with current knowledge. Even the energy required for smaller, local warp-like effects is enormous. Simulations suggest that creating a bubble capable of carrying a spacecraft within the solar system still demands energy on the scale of a star. Expanding this bubble to interstellar or intergalactic scales increases energy demands exponentially. While advanced civilizations may theoretically manipulate energy at these levels, the requirements push the limits of the universe itself. A civilization attempting to harness such forces would have to capture and convert vast portions of stellar output, store it without loss, and maintain precise spatial configuration. Challenges that seem as extreme as the distances involved. The conceptual appeal of wormholes and warp drives continues to inspire research. Scientists explore mathematical properties of spacetime that allow these metrics, examine how negative energy behaves in quantum systems, and test whether small-scale analogues can be produced in controlled conditions. Experiments with Casimir effects and vacuum fluctuations probe tiny amounts of negative energy, offering a glimpse into physics that could, in principle, support wormhole-like behavior. These efforts remain far from producing any traversable structures. The experiments probe the edges of known physics rather than build practical transport mechanisms. They highlight that the ideas exist within the framework of serious science, yet implementation remains science fiction. Galactic gravity remains a further barrier. The Milky Way's central black hole and its surrounding bulge form a deep gravitational well that influences every orbiting mass. A theoretical wormhole cannot simply bypass this structure. Launching a ship toward another galaxy through a tunnel would still require the object to move inside the galactic potential well, potentially altering trajectories and introducing enormous tidal stresses. Warp drives may avoid acceleration in conventional space, yet the ship inside the bubble still exists in a gravitational landscape shaped by millions of stars and dark matter. The universe does not flatten for theoretical shortcuts. Any travel must contend with real structures on scales of tens of thousands of light years. Hypervelocity stars demonstrate natural escape from the Milky Way, yet they operate through forces that far exceed what humans can produce. Even if a civilization had the means to manipulate wormholes or create a warp bubble, the energy and precision needed would be comparable to stellar-scale mechanics. Nature shows that massive gravitational interactions produce these extreme motions, while artificial constructs would need to replicate or surpass these energies without catastrophic consequences. The physics of high-speed escape is unforgiving. The environment of the galaxy does not forgive mistakes. These limitations help explain why wormholes, warp drives, and similar concepts remain largely theoretical. Equations predict they can exist. Solutions in general relativity describe the mathematics, yet every real-world application hits barriers that scale with mass, energy, and gravity. Even with a starship designed to exploit these phenomena, the galaxy itself forms a barrier impossible to bypass fully. Escape or traversal remains constrained by the weight of the Milky Way, the energy needed to shape space-time, and the fundamental rules of relativity. No experiment has bridged this gap, and every design remains in the realm of speculative physics. The allure of these ideas comes from the sheer imagination involved. Humans are forced to reckon with distances so vast that conventional travel seems hopeless. If a warp bubble could exist, a ship might move faster than light locally, while avoiding the relativistic time dilation that hampers near light-speed travel. If a wormhole could stabilize, it could create a direct shortcut across vast cosmic expanses. The mathematics of these scenarios inspires scientists, engineers, and dreamers alike. Yet the practical challenges underscore the impossibility of implementing these constructs in real time. Even at the theoretical level, careful consideration of mass energy, stability, and galactic gravity shows that nature sets barriers that cannot be ignored. Space is indifferent to speculation. A ship attempting to exploit a wormhole faces the same dangers that confront any matter passing through strong gravity: tidal stresses, radiation, and collisions with gas or dust streams. The bubble of a warp drive must withstand distortions caused by nearby masses, and any failure would expose the occupants to extreme relativistic hazards. Even with perfect energy management, navigating through a galaxy filled with stars, dark matter, and interstellar gas presents risks that no theoretical shortcut eliminates. Every calculation must account for the mass of the Milky Way, the gravitational pull of the central black hole, and the distribution of matter throughout the disk and halo. Humanity continues to explore these concepts through equations, simulations, and small-scale laboratory tests. The Alcubierre metric provides a playground for understanding spacetime manipulation. Quantum field studies offer glimpses of negative energy possibilities. Yet every step highlights the enormous scale differences between laboratory physics and galactic-scale travel. A real wormhole would require a tunnel long enough to traverse light years, energy comparable to stellar mass, and conditions that stabilize spacetime against collapse. A warp drive would demand energy management that converts matter into a precise spatial geometry around a ship while interacting with every gravitational field in its path. No civilization has approached this level of capability. Ultimately, these speculative solutions exist in a space between mathematics and imagination. They reveal what general relativity allows under extreme conditions. They demonstrate that the laws of physics do not entirely forbid shortcuts through space-time, yet the laws themselves impose practical barriers that scale with mass, energy, and gravitational complexity. The energy needed to generate or maintain these constructs is astronomical. The complexity of the Milky Way's gravity prevents simple traversal. Natural escape velocities, tidal forces, and interstellar hazards all combine to make implementation far beyond current or foreseeable human technology. The fascination with wormholes and warp drives continues because the universe itself appears almost unreachable. Stars burn out before journeys to nearby galaxies are possible. Galaxies drift apart faster than even near-light-speed travel could overcome. Even with the most advanced propulsion imaginable, the distances and energy requirements stretch past the scale of human civilization. Wormholes and warp drives offer a glimpse into what might be possible in theory, while simultaneously highlighting the limits imposed by energy, mass, and gravity. The Milky Way itself remains a gravitational cage even in these speculative scenarios, showing that the structure of the galaxy sets boundaries for everything, including dreams of faster-than-light travel. Every thought experiment with a wormhole or warp bubble must confront these realities. Even if a tunnel appeared, it would sit within a galactic gravitational landscape that bends and twists space. Even if a bubble moved faster than light relative to local space, it would still interact with the Milky Way's mass distribution. Even if negative energy existed, producing the scale required to maintain stability defies imagination. Theoretical constructs offer hope and inspiration, but the physics governing the universe remains unchanged. The equations work on paper, but the mass, energy, and gravitational realities ensure that intergalactic travel remains unreachable through these ideas.